Okay, good. So welcome to this afternoon session. So I will be chairing this afternoon session. So the first speaker is Tilman Fau, and he will tell us something about dipolar interactions in a different type of setup.
Yeah, thank you, Luis, and thanks to the organizer for having me here. This workshop is very dear to my heart since long-range interactions pay for my living since 25 years, as Luis can confirm. So today I thought I would tell you something new that actually, at least the second half of the talk, I have never talked about, and I'm curious what you say. Yeah. So it's about dipolar interactions, of course, but not very cold. Yeah, so very hot means either room temperature or way above room temperature. Yeah. In my institute, we are working on long-range interactions in many different aspects. Yeah, a lot of work is going on in the ultra-cold, and you have heard about these experiments with the magnetic quantum gases. We also have an activity on ultra-cold Rydberg molecules and impurities. We even have, as many people, a quantum computing activity these days. But today I want to focus on this hot stuff, yeah, which is combining hot atomic and also molecular vapors with integrated electronics and integrated photonics. Let me start, as this has not been done here yet, just by the magic of Rydberg atoms first. I don't have to introduce this in this audience, but just to remind everybody, if we are exciting, for example, with 2 photons to a Rydberg state here, yeah, then we have huge interactions between Rydberg atoms, giving rise to the Rydberg blockade phenomenon that, you know, ever since it was proposed in 2000 as a mechanism for building quantum devices, keeps us busy still today. Yeah? And that is due to the fact that this van der Waals interaction, it's a C6 interaction. Yeah? It goes like 1 over the distance to the 6th power, scales with the 11th power of the principal quantum number. And if you do a decent control of your stray electric fields, this principal quantum number in our experiments at least can be higher than 200 or even more. Yeah? So that's a huge Rydberg orbit that can be as large as many micrometers, yeah, for the electron wave function. And it's, of course, a very fragile object. Now, this Rydberg blockade, of course, was demonstrated many times in the cold atom world. Some years ago, actually 10 years ago, we set out a project to see whether we can study and make use of the Rydberg blockade effect with thermal vapor cells. Okay. And if you look at this blockade mechanism in an ensemble of atoms that are not structured by any lattice or so, just somewhere in space, and you excite them, then due to this blockade mechanism, of course, you all know, yeah, the Rydberg excitations have to keep a distance, the so-called blockade radius. Yeah. This turns out to be a length scale on the orders of tens of micrometers in the ultra cold, and on the order of 1 micrometer, if you plug in the numbers, in the case of hot vapors. Because how do you calculate the blockade radius? Well, it's the interaction strength compared to the bandwidth of your excitation. Yeah? And if it is the Doppler width, yeah, instead of, let's say, the natural line width, well, then this blockade radius will shrink. But as this potential goes down like 1 over R6, it actually doesn't shrink that much, yeah? Just from 10 to 1 micrometer. So if you build a cell, a vapor cell, yeah, which with 1 micrometer dimensions, you should be able to use the blockade to build, for example, a single photon source, or to prepare one of these W states where you have a single excitation that is shared among many atoms in the ensemble. Yeah, and this is the original paper, of course, where you see that basically what you get is an effective 2-level atom, although it's an ensemble, where the excited state is this excitation that is distributed over all atoms in a coherent fashion. Yeah? We call it a superatom. Yeah? Although it's thousands of atoms, it behaves like a 2-level system. If you combine this superatom idea with 4-wave mixing, namely you go up to the Rydberg state and you go down maybe another route here, yeah, for example, D1 and D2 line in rubidium, then you produce, yeah, then you basically copy this quantum state, this W state that you have prepared in the Rydberg state to the light field, and you can detect it. Yeah? Moreover, if this wavelength involved is smaller than the blockade radius, which is the case here, and you have an optically thick medium, this photon will come out in a directed fashion in the forward direction, and that makes it nicely detectable. And without going into any detail, just show you our self-made cells. Yeah? You can see that they are thin. Yeah? You see the Newton rings here. Yeah? So there are 2 glass plates. You can see here a stem where we are putting a little bit of rubidium. Yeah? And then with these Newton rings, you can actually measure the thickness while you do the measurement and make sure that your cell is thinner than the blockade radius. Yeah? Here is Harald and Robert filling one of these cells. Here's another example of these cells. We put this cell between 2 lenses to focus our excitation lasers down to below 1 micrometer, such that in all 3 dimensions, the volume where we excite is smaller than 1 micrometer. That's the schematic drawing of this. So the transverse size of this laser beam is smaller than the blockade radius, and the thickness of the cell is also smaller. And then in this particular example, we are exciting at the D1 line, and we are detecting at the D2 line. Yeah? We actually have a wedge cell, as you have seen. You can see these Newton rings. So when we move the cell, we can change the thickness. And that's already 5 years ago. We can then look at this emitted light in this 4-wave mixing process and indeed measure a G2 correlation function that is not perfectly 0, but clearly below 0.5, meaning that this is a non-classical light source. The brightness of this source is about 10%, so it's a deterministic single photon source with a success probability of 10%. We can change the cell length from 600 nanometers to 800 nanometers. The blockade still works, but then at around 1 micrometer, the blockade stops, and the G2 function goes back to 1. So far, so good. Yeah, so this Rydberg blockade idea works even for hot vapor. Actually, here we had to heat the cell to 200 degrees. Yeah? just to have enough optical thickness, because that's the figure of merit, optical thickness per blockade radius. And this cell was actually optically thick, although it was only a 1 micrometer or less in thickness. Okay. Now, if you want to integrate this into some photonic circuit, that would be nice, because it could be multiplied, and you would also think that these photons that are emitted are always the same photons, because it's rubidium. It's not a quantum dot or an NV center where you get different wavelengths for any defect or any dot. It's rubidium, and no matter where you buy your rubidium, it's always rubidium. And so the photons that this device is emitting are always 780 nanometer rubidium photons. So it would be the ideal thing to integrate it into one of these platforms that are going, for example, for photonic quantum computing. Okay. Now it turns out there's a problem. I mean, the Rydberg atom is large. If you bring it close to a surface, like in a photonic circuit, there will be a strong interaction with the surface that produces some complication. We can discuss how to solve this, but I want to ask another question, namely, do we actually need the Rydberg blockade for this effect, or can we get away with just normal two-level atoms that we excite from the ground to the excited state? Because we know if we do that, there's a dipole moment. And there is a dipole-dipole interaction between two atoms that are close by. Can we use that to do the same thing? And now you have to be very careful. If you have a medium of two-level atoms and you bring them very close, then they are interacting already, even if there's only a single photon. For the blockade effect, we needed two photons, right? We need two Rydberg atoms to make this excited state shift out of resonance. So clearly, this ensemble of atoms that are undergoing dipole-dipole interaction is different in nature. We cannot expect a normal blockade phenomenon from this right away. I will still tell you now that it's still a very highly nonlinear system, and how we can actually measure this is the topic of the next few slides. Of course, we need a density that is much larger than 1 atom per wavelength, actually over 2 pi cubed. Then, if we are in that regime, the dipole-dipole interaction will exceed the natural line width of the transition. Okay. So we need high densities, and it cannot hurt to enhance the dipole-dipole interaction by either cavities, that's not what we do, or by dielectric environment, that is shaping the mode functions from pure plane waves or Gaussian modes that you are usually using in your normal experiments to something else. And I show you an example in a second. This dipole-dipole interaction, just as a reminder, you can think about it like this. You have one excitation somewhere in the medium. It doesn't have a dipole moment, but if all the others are in the ground state, then this excitation will hop around, basically. That's sort of the many-body aspect here. Yes, just like in this movie, you see that if the population is either fully up or down, there's no dipole moment, but anything in between has a dipole moment, and that induces an interaction. Now, if you go to the weak excitation limit, let's say 1 photon only, then this medium is very nicely described by a Lorentz model, where you are basically treating this electronic excitation of every atom just like a little spring, where the charge is held to the nucleus. So it's a very classical thing, actually. And that explains also why the very first photon is already shifted out of resonance if your atoms are close enough together, okay? Because it's a coupled system from the very beginning, like a coupled system of antennas, for example. So that is actually Theodor Förster. I have to mention him every time I talk about this because he was a professor in Stuttgart, so in the chemistry department, by the way. Okay. So if you think about this light-induced dipole-dipole interaction, then you get a dipole field that is not a static dipole, it's an oscillating dipole. Yeah? It oscillates at the optical frequency. And if you plot the field of this Hertz dipole, yeah, it's a Lorentz model, yeah, this is how it looks like. Yeah? You have all learned about this in your electromagnetism lecture. If you put another dipole, you get a complicated expression for the dipole-dipole interaction energy. It has these nasty terms here that are due to retardation effects. But forget about them, yeah? Because if we put all the atoms, or the next neighbors, into this very small volume, smaller than lambda over 2 pi cubed, these retardation effects can be neglected, and we are back to the formula that also Lewis and others have shown for 2 static dipole moments. Yeah? It's anisotropic and goes like d squared over the distance cubed. And if you now think about an ensemble of these dipoles that are coupled this way, and you put them in 3 dimensions, you average over all orientations, the average is 0. If you put them in 2 dimensions, and the dipole orientation is like this, there's a redshift, or basically the energy is lower, yes, because of this dipolar coupling. If you put them in a chain next to each other, where they are all repelling each other, it costs energy, and you would expect a blue shift in the spectrum of this medium, okay? And I show you one experiment in 2D, or let's say quasi 2D, and one experiment in 1D, where we see a redshift and a blue shift. This is the first example. We take our thin cell, just the same cell as we used for the single photon source, and we increase the density for a short moment with the so-called light-induced atomic desorption pulse. There's rubidium sitting on the surfaces. If I apply a light laser pulse, this rubidium is taking off the surface. It increases the density for a short moment. This is the time scale here in nanoseconds. And if you then take a spectrum, a normal rubidium spectrum, and you measure the shift of that spectrum, you see that there's a redshift, yeah, of about 50 to 100 line widths. Gamma 0 is the natural line width of the D2 or D1 transition, which, of course, as the density vanishes, goes away again. Yeah? In this experiment, we achieved densities of n over k cubed. Wait a minute. Yeah, n over k cubed of 100. And you see that the shift is also on that order, yeah? 100 line widths. That's a redshift in the 2D case. Yeah? That's still not integrated in the photonic circuit. Yeah? Let's do that and make an ensemble that is very long, yes, and make a 1D chain. The way we do this is we take a photonic waveguide that is integrated on a chip, and this is a dielectric structure here and here, which guides the light along the chip. And we open it in the center, and there's a slot that has a width of about 50 nanometers only. So that's nanofabrication. We have a foundry on our campus, and we can ask the guys there to make it for us, okay? This is the cross-section of this photonic waveguide. You see this is a dielectric material, silicon nitride, or silicon. And if we design it right, then the light that is propagating is concentrated in the gap. Okay, so it's traveling where the atoms can be. Okay. We actually use rubidium as a vapor, so we put this whole thing and immerse it into a rubidium vapor, such that the atoms can make their way into this gap, and we excite them there. We excite them by 2 photons. Actually, 1 photon we know already, that's a 780 nanometer transition. This one we shine from the top. By that, we can vary the population in this 5p state at will. Yeah, we put more or less light. We can say, let's have p population in the front of the guide, at the back of the guide, anywhere on the chip. in that sense, this is going to be a reconfigurable nonlinearity. Yeah? You can put it anywhere on the chip just by shining this light on and off. And then the guided light is actually a telecom wavelength, 1.5 micrometer. And rubidium is nice to us. It provides this wavelength. Now, I told you we are squeezing this 1.5 micrometer light through a 50 nanometer gap, which per photon enhances the electric field. And that is the essence of the Purcell effect. Basically, it's like this. Yeah? So you have this camel that goes through the needle's eye. Yes? This big wavelength photon you are funneling into this slot waveguide, which increases not only the field, it actually also increases the dipole-dipole interaction. Yeah? Because how is the dipole-dipole interaction mediated? It's the exchange of photons along this waveguide. Yeah? There is a Purcell enhancement of this interaction, and therefore also the nonlinearity. Okay. The experiment is fairly simple. Yeah? We have a Bragg coupler where we go into this structure and out of the structure again. Okay. Now, first thing to observe is if we measure a rubidium spectrum at one line here, a particular line, you see it's fairly broad, a gigahertz typically. Yeah? Why is that? Well, the transient time and also the Doppler width of this is on that order. Yeah? So in terms of what you are used to from the cold atom world, it is a very broad line. Yeah? If you are coming from the quantum dot people side, that's actually a narrow line. Yes? They like a gigahertz line a lot. Yeah? And what's more?
Do you see shifts because of the surfaces, like from Kaiser?
Yes, there is a shift, but it's smaller than this 1 gigahertz. Yes, about 100 megahertz. Yeah. What's more, if we are cranking up the power now, as we are funneling these photons through this narrow gap, we can saturate, and we measure this by broadening, by just power broadening this line. That's the width. You see it's 400 megahertz at very low powers, and then saturates. And here is about the saturation intensity and gets broader. Yeah? And if you look at this axis, the probe power that we need to saturate is 100 femtowatts. That's not a lot. Yeah? That's just a few photons, if you think about it in terms of the inverse bandwidth. Yeah? If you calculate this, this is a few tenths of photons per nanosecond that is going through this device. Okay? So we are close, not quite, but close to single photon operation here, if you talk about the nonlinear behavior. So what happens if I drive this thing strongly is that I'm going away from this Lorentz model, the classical dipoles, to a situation where this shift actually goes away because all these dipoles get out of phase due to a saturation effect. Yeah? So if we measure now this shift, okay, so first I should say we measure the shift for very low powers. It's the shift that is expected from the Lorentz model. The theory is actually this blue shaded line here. And if we exceed our saturation intensity, then the shift goes away. Here is a higher density. Now it's again this density per wavelength cubed parameter. That's the difference between these two plots. That's a little bit higher density than this one. And you see here we get, again, typically 100 gamma blue shift now, because we are choosing the polarization in this waveguide like this, such that the dipoles are repelling each other. That's about the saturation intensity, or where we see that basically we have the highest response as function of the intensity. Yeah?
What is the difference between the red and the black circle?
Oh, this is just the example plot in the figure of the paper. We show this, I didn't put it here now, we show this one as an example spectrum. Yeah. So here is the summary. So as a function of density, we measure the line shift here to the blue. We again go all the way up to about 70 or 80 line widths. you realize we are not as dense as in this 2D experiment, yeah? So that has technical reasons. We are not using LIAT, for example. We are just using a normal vapor cell. So there is room for improvement, yeah? In the future, we could go even one order of magnitude higher here, yeah? But you see that if you do this Lorentz model without per cell enhancement, that's the dashed line here, you see that we are getting a shift or an interaction strength that is enhanced by a factor of 8 due to this camel through the needle eye effect, yeah, the Purcell effect. Yeah. That's an example. So I should actually sum this up and say, okay, now we have a medium, the properties of which, namely its resonance frequency, depends on the intensity. On the few photon level, let's say a few tenths of photon level, we are changing the line, the resonance by 100 natural line width, I should say. Yeah? It's still a fraction of the total line width, which is much broader for us. Yeah? But at least, you know, that's the beginning of something interesting, I would say. Yeah? So meaning with like tens of photons, you can switch this resonance of this medium off or on, yeah? Which is the basis for switching light with light, you know. Not yet fully on the single photon level, but at the tens of photon level. Good, and this is just one example of what you can do if you are sort of bringing together the possibilities of nanophotonics with atomic vapors. Yeah? The traditional spectroscopy of atomic vapors integrated in such a way, that's a real structure. Here you see these Bragg couplers, and actually this is a 3-port device. You can do a counter-propagating control laser, for example, and then do a saturation spectroscopy, if you like. If you send your light in here, and then you have the pump beam here, and then you look at the output here. That's a device. Once you have made this device, you know, you don't need to adjust anything anymore. No mirrors around, no screws. Everything is stable. You can, as I showed you, I mean, by designing these waveguide structures, tailor the atom-light interaction at will to use this Purcell effect. You can also include cavities and so on. And it is a scalable technique. I mean, in one of the cells that we are using, we have hundreds of these circuits printed. Yeah? So one cell keeps several PhD students busy for some time, you know. Good. So to summarize this first part, I showed you that in the slot waveguides, we can get on the order of 100 gamma line widths. We have seen this Purcell enhancement. We could get a density in units of wavelengths over 2 pi on the order of 7. In the previous experiment, we were with these LIAT pulses even at 100. And if you calculate now as a dispersive medium, yeah, what it takes to shift a propagating light field in phase by pi, which is what you need for a conditional phase gate, let's say, then with this kind of setup, you need tens of photons to do this. Yeah? So there's still some way to go, yeah, because we would like to do this with a single photon, yeah, in the end. And there are ways to improve the situation, either getting higher densities, getting even more fancy photonic structures, like these so-called alligator resonators. I was told in, where is Blair, in New Zealand or in Australia, alligators and crocodiles are different things, right? And so not sure whether alligator resonator is a good word, but huh?
They're also different here.
Aha, they are also different here. Okay. Anyway, I'm not the expert on this, so.
Crocodile, you wouldn't live to tell the tale.
Okay. Anyway, what's important are the teeth here. Yes. And if they are periodic, then it's like a Bragg reflector, and you make up something like a cavity to increase this Purcell effect even further. Okay, this is the team of people. It's actually some time ago, and I should mention that Hadise Alayan at Purdue is a team member and still attending all the group meetings with us, and so does Charles Adams. And I should mention, I mean, it's actually an older picture. Yeah? I mean, Florian has graduated, Arthur has graduated already. These guys have been bachelor and master students only. The current team that is working on this is actually Annika and Max and Felix here. Yeah. And Benjamin is the guy who's making the structures in the foundry. Yeah. Good. Yeah. That was the first half of the talk. How much time is left?
6 minutes.
6? Oh, that's not a lot. Good. I wanted to talk about molecules as well. Actually, I changed the title slightly for this part. Namely, I talk about charge dipole interactions between Rydberg electrons and molecules. Yes. I mean, we're talking about dipole-dipole interaction. It falls off like 1 over r to the 3rd power. But if you think about the interaction of a charge with a dipole, it goes like 1 over r squared, even more long range. Yeah, that's fun. We should do it. Okay. So this goes back to a discussion I had over time, many years now, with Hussein. An experiment that we started on nitric oxide several years ago, about 3 years ago. And Hussein and Rosario and Janine, they came up with this beautiful idea to make molecules of molecules that are bound by the charge dipole interaction. Okay. Nitric oxide, NO, has a dipole moment. Yeah, it's a heteronuclear molecule. It's a small dipole moment. Yeah, it's 0.16 dBi, which is actually smaller than this so-called Fermi-Teller limit, where you get a bound state, from which on you get a bound state. Still, there exists NO minus, yeah, so the anion. So if you scatter an electron from that nitric oxide, you will get an, I would say, unpredictable interaction at first. Yeah? So you have to measure something. So the question is, can we observe these objects? Okay. And I should tell you, but I have no time to go into the detail, that actually our motivation initially was very different, namely to detect the NO in the human breath as a medical diagnosis thing. That's this thing, but ask me about it later. So our measurement principle is the following. We take NO from a gas bottle, send it through our setup. We excite it actually with 3 photons to the Rydberg state. This Rydberg state collides with the background gas. The charges get released. You get an electron and an ion. If you apply a small electric field, they are pulled to some electrodes, and we measure a current. Okay, that's this thing. These charges are going to be measured with 2 plates, just a capacitor, and we measure a current. That's an optogalvanic spectroscopy method, I would say. Yeah? Some sort of variant of this, sort of old-fashioned, but very, very sensitive, as you will see. This is the cell. You see we are filling NO in here, and it flows through to the other side. We have an electrode here. That's the gold-plated thing here. And we are exciting this from the side. Okay. And you see it's important to have a transimpedance amplifier, TR, very close by to your current source. Okay. And the fun fact of this is that these TRs these days, using fancy pseudo-resistance techniques that I cannot explain to you, we have a collaboration with some guy in the electronics engineering department that is making this chip for us. They have a noise floor of 10 femtoamps per square root hertz. Yeah? That's a small current, right? So if we send in our lasers, our 3 photons, yeah, first of all, we need a 226 nanometer laser. That's, of course, a broad transition, yeah, because it's a thermal ensemble. Yeah, we have a large Doppler width, yeah, several gigahertz here, actually almost 3 gigahertz. But then this UV laser is a CW laser. It selects the velocity class. If we then excite it to the next higher lying state, which is this so-called H state here, the line becomes very narrow if we are scanning the green laser. And then finally, we go to the Rydberg state with the 835 nanometer, and we get some spectrum, some Rydberg spectrum. Actually, you see the currents here. Yeah? already here we get picoamps, and then up here we get nanoamps. Yeah? Remember, femtoamps per square root hertz is the noise level. So we have a very good signal to noise. I can go into the detail of the molecular physics. Maybe I skip this. There are various channels, of course, for the Rydberg excitation. This is how a Rydberg spectrum looks like if you take it. You see there are actually two series overlapping because of different rotational states now of the nitric oxide ionic core. There's one for the rotation quantum number, that's actually Hund's case D, yeah, in the Rydberg state, 5. And you can assign these numbers here, and you see principal quantum numbers go up to 60 or something. And there's a second series here, which is the other rotational quantum number of the inner core of the molecule that is excited, and we go up to, yeah, again, 60 or something like this. Yeah? So now let's look at one of these lines. Maybe this one here, and we see there are two lines here, 61 belonging to the n equals 3, and the 41 belonging to the 5 rotational quantum number, and apply an electric field. And we see a Stark map, yeah, of this NO Rydberg molecule. And you see familiar stuff, yeah, like this is the hydrogen-like fan that spans in the electric field. And if you have good friends, not only Hussein, but also Stephen Hogan and Matthew Raymond, his student, then they can come up with a theoretical prediction for this Stark map. And it fits fairly nicely, actually, I must say, even in some details like this. Here's another measurement. This is a measured Stark map. It takes about an hour to measure this. Yeah? And you see it's basically no noise. Yeah? It has a current here of half a nanoamp. And you see the high L states. And now you see also, again, the hydrogen-like zero quantum defect Stark fan. And you can see that this kind of measurement is well suited to measure the quantum defect of these states. Yeah? The H state, for example, the G state, and the F state. Yeah? If you come from a rubidium or an atomic site, the quantum defect already for the F state is negligible. Yeah? It's very small. Here it is sizable. Why is that? Well, a rotating molecule is just a bigger object than an atom. Yeah? Now these quantum defects are going to be dependent on the rotational quantum number, yeah? Because the faster you rotate, the bigger the thing gets. Yeah? So you have to do some systematic measurements of these quantum defects as a function of this rotational quantum number, 4 in this case. So work in progress means we are taking a lot of these Stark maps right now to just measure those quantum defects. That's a prerequisite for stuff that is going to happen soon. So, but I want to point out this state here is the one that has no dipole moment along the electric field direction. That's why it is the most narrow line in this spectrum, because we have a little bit of inhomogeneous electric field. So we get a narrow feature here. The line width of this is about 100 megahertz. And we can now measure the pressure shift of this line, okay, and the broadening. Now this is a very old topic. Yeah? Measuring pressure shifts and broadenings started actually the whole field of Rydberg spectroscopy in the 1930s. Amaldi, Segre, Fermi, and others pioneered this by looking at Rydberg lines in discharge lamps. Okay. And that's how the concept of the scattering lengths actually was introduced to physics in general, actually. Yeah. So you get an interaction of the Rydberg electron with this polarizable atom, that is maybe your background gas, that is proportional to the density, yeah, and to the scattering length. Yeah. If the scattering length is positive, you get a blue shift. If it's negative, then you get a red shift. Okay, so here is some data from this Amaldi-Segre paper. Yeah? This is the interaction in 300 gigahertz units here. And this is the density. So they were working at atmospheric pressures. But you see a nice linear behavior. And it doesn't matter whether this Rydberg electron came from a potassium or a sodium atom. Yeah, it's just this electron is so far away from the core, it interacts with this polarizable background, and in this case, it was a hydrogen molecule. Yeah? Here's another plot which I find interesting from a German group in 1934. They measure this red shift and the blue shift as a function of principal quantum number for background gases of different kind. Yeah? Helium, blue shift. Neon, no shift. Argon, red shift. Okay, and that just tells you this scattering length can be anything. Yeah? Now here's our measurement. The interaction of rubidium, so these are older measurements that we did some years ago, just as a reference now. As I said, doesn't really matter where the electron comes from as long as you understand the orbital. Interacting with argon, and you see there is a little bit of redshift as in these old measurements. And here you also see the broadening. Yeah? The broadening in this case is actually on the order or a little bit smaller than the shift. If you take a background gas that is nitrogen, okay, you get almost no shift here, as also in these old days was already known, and some broadening here. And now we do the same experiment with nitric oxide. To my knowledge, that was not done so far, because nitric oxide is not something you pour into your discharge. Yeah? It's a reactive gas. Okay. So what we see there is a shift that goes to the red. Actually, that's all the same scale. So it's almost like in this argon case here. Yeah? But what you observe is that the broadening is tremendously larger than in the other cases. And what is new here now is this is a C2 interaction, not a C4 interaction. Yeah? So it's like a charge dipole interaction, which is stronger than the interaction of the charge with an induced dipole. Yes? So we see this just by eye, yeah? Let's say. Yeah? We get a very large broadening. Why is that? Why do we actually see a broadening and not just a very strong shift? The reason is simple. Yeah? It's a thermal gas. And the distribution of the rotational states is thermally populated. So our perturber in the Rydberg orbit, although we know this orbit very well and know all the quantum numbers, this perturber here is in a mixed thermal state of all possible rotational quantum numbers, described actually in Hund's case A by the quantum number J here. Yes? And you see, yeah, in principle, we have a mixture of all these different rotational states in our signal. And now, of course, what needs to be done in the future, and that brings me to the end, that's already the outlook, Louis, is that we are selecting a single of those rotational states. How can we do that? We need to modulate a property of this rotational state, for example, a rotational transition, and demodulate it with a lock-in amplifier. If we have enough signal to noise, and I hope I convinced you we have a lot of signal to noise, we are quite confident that we can single out every single individual rotational state and then measure not the ensemble average shift and its broadening, but individual lines that are depending on the rotational state. And that brings us then to this figure from Hussein and Rosario's paper, where they predict actually binding energies for those no-no molecules. So this is Hussein's invention, a molecule of molecules, which are on the order of a few hundred megahertz. Yeah? This resolution we certainly have. Yeah? And so we are discussing this also as we are here. Summarizing, we do high-resolution 3-photon Rydberg spectroscopy with these no-no molecules. We measure the Stark maps, and we do systematic studies of all the quantum defects there, and have detected the pressure shift and the broadening for the thermal ensemble, and hopefully in the future we can single out a single channel there. And I should not end without thanking the team. I should say this is really the work by Fabian Munkes. Yeah, he is an outstanding PhD student. Harald and I, we have the pleasure to supervise him. And the other guys, they just started their bachelor thesis just a few weeks ago, and Alex started the master thesis also just a few months ago. Thank you for your attention.
Thank you, Tilman. So we have time for a very quick question, if there's any.
I just have a technical question. I was amazed about how well you can put the light into your nano structure. And I was wondering how much of the light field travels in these dielectric rods as compared to what's really inside the slit, and how does that go into impedance matching?
Okay, so the question is about this structure here, and I showed you this cross section, this one here. So if I calculate the Purcell effect in here, just locally there, I get an enhancement of about 35 or 40. What we measure is 8. And the reason for that is, that there is interaction also with these other, with the other evanescent field available. So yeah, in that sense, not all the light is going through that channel. Yeah.
Okay, and you see that
but we see an average effect over the whole mode that is still a factor of 8. That's the measured value. Yeah.
Thank you very much. So I think we should move to Igor's. Let's thank Tilman again.
Nee, ich glaube nicht. Okay. Das ist aber deins, oder? Okay.
So the next speaker is Igor Lesanovsky from Tübingen, and he will be talking about time crystals.
Okay. Oh, sort of. Okay, buy me some time, Luis. I need to set up still. Okay. Test. Okay, you hear me? How's this work? Yeah. Thank you very much. Yeah. To the organizers, for having me here. So it's always a great pleasure, obviously, to be here. And I have to be careful. Slightly claustrophobic, I have to say. But okay, I'll do my best not to collide with the ceiling. It's a pleasure to be here. It's okay, it's okay. Oh God, it's a bit scary. So it's a pleasure to be here. And I'm going to talk, as Louis said quite rightly, about time crystal phases, fluctuations, and quantum correlations in spin boson systems. So a little bit of everything. And there will be a lot of connection points, I hope, to, well, the talks we have been witnessing this morning and also talks later, thank you very much, in the workshop. Just for those of you who don't relate to Tübingen at all, well, at least you have to understand where Germany is, then you are in the game. So, so Tübingen is in the south, so the blue thing is Germany, Tübingen is in the south, so it's very picturesque, so it's like an old medieval town from the picture books, let's say. It's very nice, and I'm happy about being there, obviously, but I'm even happier to collaborate with a great bunch of people. So the stuff I'm going to talk about today will have been produced by Albert, Federico, Marcel, Robert, and Bea. And let's just jump straight in. So very briefly, I will talk about open quantum systems at the beginning, about spin boson model, so why this connection, then quantum master equation, and how this derives under certain circumstances from spin boson models. I will talk about feedback control. It's actually not necessary, the feedback, but it's actually fun to think about it, and you will see that one can use it to shift around phases and phase transitions in these quantum optical systems. It's quite neat. Then I will talk about waveguide quantum optics, because this is the setup parts of the talk are based on, and which is also the scenario, the platform that gives rise to the long-range interaction, which kind of inherits the title to this workshop. I talk about coherent interactions and dissipation, well, collective observables, and in the thermodynamic limit, how they, so to say, give rise to a mean field description of the system. Then we'll talk about dynamical phases, phase diagram, spin squeezing, which you get for free, which is quite nice. And then later, let's see, so you see there's no outlook yet. I will talk about other systems doing this interesting stuff in cavities and also in free space. So let's see how far we get. So just why spin boson model? Well, I would say one can argue that spin boson models are at the heart of almost everything. And for sure, our beloved quantum optics and atomic physics is captured to a large extent by spin boson models, where, well, spins are typically modeled by two-level atoms, or are representations of two-level atoms. The Hamiltonian is given by this expression here, where it's just describing the energy difference between those two levels under considerations. And then you have bosons, and one prominent, let's say, manifestation of bosons is the electromagnetic field, in which we typically immerse our atoms. And this electromagnetic field is, of course, described by such a Hamiltonian here, where A and A dagger are the annihilation and creation operators of, well, photon excitations, as you wish. And then you can look at the interactions, and then at the most basic level, we have dipole coupling. So the atomic dipole, so the transition dipole element, is coupled to the electric field at the position of the atom. And then you, of course, can write this down in this fancy operator language, where you see that in the end, everything is determined by this coupling constant, which tells you how strongly these raising and lowering operators related to electromagnetic field couple to the atomic dipole, represented by these Pauli raising and lowering operators. Okay, so this is why spin boson models are at the heart of everything. But of course, we will do some simplifying steps. But before we go into this, just some basic truths which will, so to say, guide us through the talk. So, well, interaction between atoms and light mediates dipole-dipole interactions. Tillman showed this very nicely in a slightly different representation. But at the end, this expression for this electric field that you showed is exactly coming out also of this formalism. Also, this funny modulation as a function of the Q times R that you have seen there. So the point is also that interactions with the electric that are caused by the electromagnetic field are not only coherent, so they are also dissipative. One prominent dissipative effect is, of course, spontaneous emission. So we know that when we have a two-level atom, or any atom immersed in the electromagnetic field and prepared in an excited state, it will decay to the ground state. And this, of course, is a dissipative effect, which you also have to include if you want to look at the evolution of these systems over long times. And, well, then the third truth, and this is probably the most interesting one, also for the purpose of this talk, and also Tillman, I'm very grateful that you dropped all these ideas already in this talk, depending on the mode structure of this bosonic field, whether, for instance, you put the atoms close to a surface, or inside a waveguide, or near a waveguide, or inside a cavity, the structure of these interactions, and for that matter also the structure of the dissipation, will change, and is strongly affected by how these modes are shaped that predominantly couple to the dipolar transitions within the atoms. Okay, so then there's a lot of math to be done in order to simplify the problem. And let's say under reasonable assumptions, what you end up with for this type of quantum optical system is a so-called master equation. Lindblad master equation, which many of you have most certainly seen already, describes the evolution of the density matrix of the atomic ensemble. And this is governed by a coherent evolution, mediated by a quantum Hamiltonian H, and some dissipator, which is composed of these so-called jump operators Lj. Just to give a simple, so to say, picture of this, in case of one two-level atom immersed in the radiation field, so we have and laser-driven. So we have here a Hamiltonian that describes coherent laser excitation of this atom in resonance. It's just the Rabi frequency times the sigma x operator, and then you have this dissipative effects, which are modeled by this, or described by this jump operator, which goes here as the square root of the emission rate, kappa, and, well, the sigma minus operator, that when you let it act on the excited state of the atom, will demote it to the ground state. I think we have seen this in some or other manifestations. Good. Okay, so now, this is our, let's say, open system that is described by this master equation. So think, for instance, in this particularly simple case that I showed you before, of the system as being an atom, two-level atom, and it depends on certain parameters, for instance, like the Rabi frequency, and this atom is immersed in the bath in this radiation field. This we have integrated out Yeah, so in principle, we can live without taking an interest in it. But what we can, of course, also exploit is that this effective evolution of the system under the master equation is obviously caused by the fact that there is exchange of excitations or particles between the system and the bath. This is the reason for which the system doesn't undergo a closed Schrödinger equation evolution, but undergoes an evolution that is described by a quantum master equation. And what we can, of course, do now is we can look at what is happening in the bath. Yeah, well, let's say in a less abstract way, and relating to this example with the atom emitting photons, we can look at photons that are being emitted by an atom, and we can detect them. And based on the detection, we can now do something to the atom again. Yeah? For instance, change the intensity of the laser, apply quick pulses. This would be all manifestations of a feedback scheme. Yeah? And now the question is, how can we use this kind of feedback at the level of, let's say, quantum optics, quantum many-body physics in the quantum optical domain to do something interesting. Yeah? And to, for instance, steer such a system, which is for sure then not a single atom, but a collection of atoms, into a stationary state that is in some sense interesting. Yeah? So this is the kind of story that I want to convey. So and first, what we have to do is to think a little bit about feedback and okay, what is possible and at least from the theoretical side can be done in order to describe it. I mean, this is of course all or to a large extent already discussed in the literature here. This is a very nice book, Wiseman and Wilburn, about this quantum measurement and control. But it's also nice to just to think about for 30 seconds here of what this kind of inclusion of feedback entails. So, for instance, we can, for the simplest case, which we will not use actually in this talk, we consider photon counting. But this is something conceptually simple. Yeah? Whenever there's a photon arriving at your detector, and from a theoretician's perspective, this detector is 100% efficient. So every time a photon is emitted, I actually register a click. So what I can do is I can then immediately apply a pulse, a laser pulse, to the atom. And this I could, for instance, express technically through such a term. Yeah? So remember this master equation, we had the so-called quantum jump term. I forgot to mention this explicitly, but for many of you have seen this, I think. So you see this is the process that happens. This is kind of an operation on the density matrix of the state that makes the state of the atom collapse. So this jump operator acts from the left and from the right. And what we just do with the feedback is that after this collapse, we apply, for instance, a unitary rotation here, so a quick laser pulse of area G to the atom in order to change its state. So this would be a feedback scheme where you immediately change the state of the atom after having registered a photon in your detector. So I think conceptually this is quite easy, and yeah, I think we can all agree that this is actually doable, so to say, at the theoretical level without great effort. So then it becomes a bit more difficult, or involved when you change the detection scheme. Yeah? For instance, this photons, you cannot only detect them, so to say, in terms of intensity, but you can also detect the electric field, the so-called quadrature, by coming up with some scheme that requires the imposition of another external reference field. But okay, those are details. But what matters is that what you register then is the electric field in the detector at time t. And this is a noisy signal. So this is a fluctuating quantity, with some noise around an average. But okay, this is, so to say, a theorist's impression of an amplitude of an electric field that you would detect. And now what you can do is you can now change also the laser, the Rabi frequency, the laser strength, as a function of this so-called photocurrent that you register via this homodyne detection scheme. And for instance, you can say, well, here's my photocurrent, and then there are some numbers to get the units right. Here's the rate, and here's the coupling strength. And you can ask what is happening to the system. So, and again, if you look at Wiseman and Wilburn, they tell you exactly what to do. So the photocurrent can be calculated in this way. So it's kind of an expectation value that you calculate for system observable, this is just a sigma x plus some noise. Yeah, this is exactly what we see. And if you hack everything in, yeah, into this formalism, you find that in the presence of this feedback protocol where you modulate the laser in a way that is proportional to the current that you are detecting, you have to not only modify this quantum jump term, but you have to also modify the Hamiltonian and the jump operators. So this is just a prescription that you end up with. Okay, details. Okay, keep that in mind. Yeah, so this is still in Lindblad form. This is the simplest thing you can do, let's say. There are lots of approximations in this. Please, let's not talk about this. Yeah. So, but conceptually, this is what is happening. So, okay, please keep this in mind for a moment. Feedback allows us still to use this Lindblad formalism to describe the open system dynamics. Only the feedback changes the Hamiltonian and the jump operators as a function of the feedback strength, so to say. So the system where I want to implement this is depicted here. So it's a chain of atoms that is positioned near a nanofiber or a waveguide structure. And this is exactly linking to what I said before. This is a means to shape the modes of the electromagnetic field so that not everything is just, so to say, described by, quotes, boring dipole-dipole interaction. Of course, dipole-dipole interaction is also present here, but here it does not decay as a function of the distance. Here it's mediated by modes that are extended over the entire system, and you essentially end up with an all-to-all interaction, which is kind of the extreme case of long-rangedness that we want to study and discuss in this workshop. All right, so let's talk a bit about the dynamics. We can also describe it to a good degree of approximation within this Lindblad formalism. Just want to talk you through the individual components here of this master equation. So you have a laser that excites your atoms from the side, and well, you have the laser detuning and you have the laser Rabi frequency. This is just a generalization of what I showed before of the Hamiltonian to the many-body case. And then I have this interaction, yeah, which is here taking place between the atoms, and it has this particular form, yeah, it's very reminiscent of what Tillman showed. Yeah, so you have this flip-flop. Yeah, one atom can, so to say, de-excite, and another atom can excite when it absorbs the photon that was emitted by the atom that was de-excited. But here's not, so to say, a modulation in front that goes with 1 over r cubed. It's just flat, essentially. So there's a constant, and then there's this phase factor here. Yeah? And this is just due to the fact that the mechanism with which the atoms interact in this waveguide is through photons that are actually propagating in its waveguide. So the field strength, let's say, of this photon is everywhere the same. So this is why we don't have a modulation. The only thing that is making this whole interaction distance dependent is basically the phase that you get while propagating through it. Yeah? So these are these e to the k. My pointer just died. No. These are these phases here that depend on the interatomic distance. So, and then, so this is the interaction. And what you also have is you have emission. That's what I said. Decoupling to the electromagnetic field doesn't only give you, so to say, these interaction effects, but you can also have decoherence. And here you also have dissipation, but also the dissipation is special. So you can calculate it or model it with jump operators that are collective. So this is just not a sigma minus for atom 1 and a sigma minus for atom 2 and so on and so forth. These jump operators, yeah, and there's one for a left propagating mode and one for the right propagating mode, are collective in the sense that they are just a sum of single atom jump operators with prefactors that again come about due to the fact that we pick up this phase due to the propagation of the photon in the waveguide. Yes, there are two questions. Yeah, please.
Should I think about n atoms or like 6 or like how many?
N equals 6 is also good. No, but we will go to the thermodynamic limit. But again, I mean, take it with a grain of salt. So I mean, obviously, when you build it in the lab, well, I'm saying obviously. So without the obviously, when you build it in the lab, you have a finite number of atoms. Later on, when we do some theory gymnastics, we let n go to infinity.
But realistically, how large is it? How many atoms can you couple in this?
there's an experimentalist in the room that can answer this. I think, I mean, most would say familiar with Rauschenbeutel experiments, and that's, well, I think on the order of 10, 20, 50, yeah, something like this. Well, it depends how well you can position those. I mean, I'm really talking about the lattice, and I'm thinking these lattice experiments are not done with thousands, but not too small, let's say, larger than 6. So, and then there's also this emission into unguided modes, which we will not talk about. We'll come back to this later, which is, of course, a problem, but nothing that, let's say, is unsurmountable.
Sorry, what sense K? I think you might have already said this, but
Say again, what?
what determines what fixes K? It's a waveguide, right? So K is a continuum of modes.
Okay, good question. So this is the K that corresponds to the wavelength 2 pi over lambda of the atomic transition. There's actually a modification due to the index of refraction within the waveguides, but let's say to 0th order approximation, it's just a...
About resonant interaction.
Yes,
between the atoms.
yes, indeed, yeah. No, of course, you have to, shouldn't say, of course, again, you have to build the system such that you are compatible with the atomic transition. Yeah? Also, these photons that are scattered from the atom, they have to be the ones that are guided by the waveguide. Yeah?
There's also guys that are not exactly in resonance, right? There's a sum over modes that sort of peaked at the resonance. So are you treating that, or are you just approximating?
No, I think you can really make these waveguides such that you have 2 modes. I mean, in the ideal case, yeah, that are guided, and the rest are free. Yeah, they are modified also by the presence of the waveguide, but they are not the ones that are actually guided. I mean, they are nano fibers, for instance, in the case of the Rauschenbeutel experiments. Yeah. Okay, so let's simplify this, and I really have to be conscious of time. So now some drastic simplifications. Yeah, so this was just the motivation telling you that if you wanted it to be more complicated, you can have all the complications there are. Yeah, but now we are doing some drastic simplifications. So we say first we neglect, as I said before, emission into unguided modes. And then we say that the atoms are positioned next to the waveguide in a way that they are commensurate, that the spacings are commensurate with the wavelength corresponding to the emitted light. So then there are lots of simplifications. So the interaction term goes away. You would think, okay, this is bad. No, it's not. It's actually good. Yeah. So, and then the only thing that remains is essentially just a bunch of 2-level atoms that you are resonantly driving with a laser. We also put everything on resonance, so there's no detuning. So, and now it's important what we do is we now implement a measurement, yeah, on the right-hand side, on the right output of this waveguide, where we do this homodynamic detection and then change the laser Rabi frequency proportional to the output signal that we detect here, yeah, and crunch everything through the formalism. And what we then get is a master equation that depends only on collective spin variables. So it's always the sum over sigma matrices that enters the description. All the operators are composed of sums of sigma matrices. So not, let's say, the atoms lose, so to say, their individual identity and everything, so to say, closed expressions in a closed expression formulated in terms of this, yeah, angular momentum, big spin angular momentum variables. So this is the equation that you get, yeah, when you crunch this through the formalism. And what you find here is that you get a feedback generated term in the Hamiltonian, and you get some modified jump operator here with jump operators that now depend on this feedback strength G. Yeah, and you see this is the jump operator that is actually related to the detection of the photon here on the right output port. So if you look at this one here, which refers to the detection of the photon on the left output port, it's actually not modified. It's just a sigma minus operator here if you add these two things together. Okay, so no feedback condition on photons emitted into the left propagating channel. And now we go to the thermodynamic limit because, well, now we want to have things simple. So in order to do this, we introduce so-called magnetization operators, and these are operators which are given by the angular momentum operators divided by n. And in the limit in which n is large, these operators, these magnetization operators, become actually classical variables in the sense that their commutator again, in some well-defined sense, on a certain set of states, yeah, so take this with a grain of salt, their commutator becomes 0. So, and then you can prove that actually in the thermodynamic limit, you find that this evolution of the system is governed by a set of mean field equations. So there's a small caveat. Well, it's actually also not something that you find totally shocking when you have been working in this field for quite a while. You have to rescale the emission rate here, this gamma, so this is the photon emission rate into these guided modes, in a way that you divide it by n. So why is this? Only if you do this rescaling, you approach a well-defined thermodynamic limit. This has just to do by looking at how these terms in the master equation scale when n grows big, and you want to have something in the end that is intensive. And long story short, you only get this when you do the rescaling. This is, of course, important for experiments. I hope we get to this. I have to see. Yeah. So, but from the theorist's perspective, it's a completely accepted approach. But if you really want to do something in practice, you have to take this into consideration. And now you get these mean field equations, which I said are provably exact. And you can now look at the mean field phase diagram. Let's say it gets interesting at some point. I mean, I think so far we can agree there's maybe the entertainment value is limited. So mean field, many of us can do. Yeah, it's nice that one can prove that it's exact. But okay, so what we knew that before from numerical simulations that can be done very efficiently on this kind of systems because everything is governed by this macroscopic spin variable. But what we find, and this is maybe the first thing we start with now, is a mean field phase diagram that looks like this. And we have 3 phases. We have a stationary one here where this magnetization is 1/2. We have another stationary one when the magnetization is minus 1/2. And this is where I want to start, so to say, the discussion. So, and we move here to a feedback strength of 0.5 and look at the position in parameter space, which is represented by the square. And then we find very nicely that the system really, when we let it run, approaches a stationary state. And just to say as a visual corroboration of the fact that mean field becomes exact, ultimately here's the simulation for different system sizes, and you see in a credible way this converges to this infinite size limit here. So then you have a phase which is actually on average 0 magnetization. I say on average because if you look at the thermodynamic limit, you find that you have actually persistent oscillations. This is the so-called time crystal. I mean, if you want to call it time crystal, I also don't care. I mean, it's a nonlinear system that you can solve, and you find a regime where you have not a stationary state. This is not so much the point. It will become more interesting in a couple of minutes' time.
Like a limit cycle.
This is a limit cycle, exactly. It's not, so to say, you see, it's not monochromatic in some sense, so there are more higher frequencies there. But funny thing is that at this point you find that this is really a limit cycle which has only one frequency, namely the frequency of the Rabi frequency of the laser. So this is what you could control with the feedback.
And why then is dumping to the extreme?
Exactly. So this is. Thank you very much for this question. This was not choreographed. So the damping is for. You get your $10 later outside. What happens there? These are finite size effects, and you find that you get. I don't know whether I've seen. Yeah, when you look at the, so to say, the spectral gap of the system in this oscillating phase, then you find it scales as 1/n, the particle number, and you decay, so to say, on a time scale that goes with 1 over the particle number. It's actually super interesting if you look at, I'm probably not getting to this, if you look at single trajectories. I mean, it's a bit like a laser. You can imagine this. I mean, it's not at a single frequency, but imagine this is just the average value. So what you would observe, let's say if you were to, for instance, to look at the photons that are output by the system or the current, that photocurrent, you would see oscillations all the time. But the damping is happening due to the fact that you have phase slips every so often. At the end, when you look at the average, you have to sum over everything, and there's a certain coherence time, right? And beyond the coherence time, you see that you go to, let's say, a stationary state, which is then unraveled as a, let's say, superposition or mixture, maybe better, of many oscillating solutions. This is how you can rationalize this stationarity. But at the level of individual realizations, you would see that you always have these oscillations. And then you can analyze these phases, and you find, okay, in the stationary phase, you're gapped, you are independent of particle number, then there's a critical point between the stationary phase and this limit cycle or time crystal phase. And at the critical point, you have another scaling as 1 over square root of n. This has been known. I mean, I would not even say 2018, so since the 80s, I would say, if you look at the literature. Now let's make this a bit more interesting. So what about quantumness? So, okay, because there's always this criticism, and to some extent I share it also, that there's some bogus, this time crystals. Maybe we hear about this also. In the end, it's just mean field, nonlinear dynamics, so what, who cares? But the nice thing is that you can now go beyond this. You can really ask, okay, what properties do the fluctuations of this state have? So what can I say beyond mean field? And this is actually very nicely doable in the framework of so-called fluctuation variables that you can introduce, which are now, so to say, the next thing you attach to these magnetization operators. So they allow you to go further in the description of the system in the sense that you can now capture fluctuations. And you see they're quite intuitive here. You take the component of your angular momentum operator, subtract the average value, and divide by square root of n, which turns out to be the proper scaling for describing this. And then you can write down with this the so-called covariance matrix. And you can look at commutation relations. It will just get interesting in a second. And you see these commutation relations between these fluctuation variables. Okay, there's something. There's some matrix here, S alpha beta, which parameterizes the commutators among these different fluctuation variables. And you see this matrix S that here describes, so to say, or parameterizes this commutator, depends on these mean field solutions, the mean field magnetizations. So what you can do now, it's a bit like Holstein-Primakov, but I would say a little bit more better controlled. What you can do now is you can go to a new basis where this matrix here becomes diagonal. And this is a basis where you move, co-moving with the mean field solution. That, okay, if you're in a stationary state, you don't have to move because you're stationary, but when you're oscillating in this limit cycle case, you have to move your frame of reference. So that this mean field is always pointing in that direction, and then you have fluctuations in the transverse directions. And in this rotated frame, what you can do is you can actually see that these operators, these fluctuation variables, they can be interpreted as momentum and position. So as bosons, you can also do this. And you can rescale them in a way that you get these canonical fluctuation, canonical commutation relations. And now you are immediately in position to ask about the quantum properties of the state. For instance, squeezing. In this XP plane. No, I mean, okay, for states, we can, let's say this is a prototypical squeeze state. You see there's an elliptic, you have squashed or more minimal uncertainty in one direction than in the other direction. And you can ask, and these states are important, for instance, for quantum enhanced sensing, because you can imagine that when you measure now in this right direction, the projection noise is strongly reduced in this direction compared to the other. This is why these states are useful. And now you can go back at this phase diagram, but you do not calculate the order parameter, so the magnetization, but you calculate the squeezing parameter as a function of the feedback strength and the laser driving strength. So spin squeezing is always present when the squeezing parameter, which basically is the ratio of these principal axes, is below 1. And let's now look at what happens, where this happens. And you see now, if you move along the same track here for the same feedback strength, from the bottom to the top, you find that in this stationary phase, which we here call squeezed phase, you see that the squeezing parameter goes lower and lower. The closer you get to the transition, the closer you get to the transition, the more prominent also finite size effects become. But if you happen to go to the thermodynamic limit, you see that in the extreme case, when you approach this phase transition from below, from the stationary phase, the squeezing becomes infinitely good. Yeah, it approaches zero. So you get a squeezed state, and you can check this also numerically. Yeah, so you really get as a stationary state, a pure state, which in the thermodynamic limit happens to be a perfect squeeze state with arbitrarily good squeezing the closer you are to the phase transition. So basically at the press of a button is maybe too much to say, you get this state which in principle would allow you for implementing quantum enhanced sensing schemes. So there are some papers about this on the archive by Matteo Paris and Diego Porras, which look at this phenomenon in this model. I'm still a bit skeptical, but I'll come to this in a second. I don't know, Louis, you have to tell me.
You have in principle 4 minutes, but since there were questions,
okay. Okay, but I will pick this up later, but I think, okay, what you can already save on the hard disk is, okay, squeeze state for free. And the squeezing gets better the closer you are at the transition. So now, what you can also do, and this is why I like this theoretical approach so much, is you can now really look at what is actually the dynamics under which these fluctuations evolve. We have already identified them as some kind of, well, bosonic operators or X and P operators in this plane, but we can ask also, how do they evolve in time? So what equation of motion is governing their dynamics? And this is just, so to say, a fun fact. You find again that this equation of motion for these fluctuations, so in this plane, perpendicular to the big vector that, so to say, determines the order parameter, that these fluctuations also evolve according to a dissipative dynamic. So this really looks like the dissipator of the master equation. But these jump operators here, they're actually time dependent. And they depend on the instantaneous values of the mean field solution, which is also kind of nice. Yeah? So it's a master equation, but it would not be, let's say, considered a Markovian master equation because there's this explicit time dependence of the operators and rates. And this allows you now also to study the evolution of the density of the elements of the covariance matrix just very briefly. Yeah? You see here again clearly these two phases. Yeah? Time evolves, and when it evolves in the stationary state, nothing is really happening to these two directions of the covariance matrix, whereas in the time crystal phase you see these growing covariance entries, which basically tell you that fluctuations grow without bound in the time crystal, which also implies that it's probably not super useful for some quantum enhanced sensing protocols. And you also see this here when you now at the critical point look at the entries of this covariance matrix. So one entry shoots up with T, one entry goes down as 1 over T, and this is the origin of this ellipse that forms. Yeah? One principal axis increases, one principal axis decreases, and this is why you get then this perfectly squeezed state with squeezing parameter 0. So you can also see this in other systems. Obviously, this maps 1-to-1 at the level of the theory, also at atoms confined in cavities, where you have here an external laser coming from the side, you have these two-level atoms, and you have here just one cavity mode. And you can also, in this case, introduce loss, which we need in order to get a stationary state through, for instance, loss of cavity photons for just non-perfect mirrors. This again, we have seen, and we will see in the course of this workshop, can be formulated in terms of a master equation here, where we have the Hamiltonian that describes the atoms in the cavity also by this macroscopic spin observables and also the photons of the cavity. And you see here this usual coupling, this Davis-Cummings model, with also a coupling that is parameterized as this 1 over square root of n to so to say, make the thermodynamics right in the sense that everything has to be intensive. Sorry. And then you have here dissipation on the photons due to this loss channel. This can be mapped, and I don't want to lose too many words about this, by means of adiabatic elimination also onto this previous model that I discussed, this model that gives this boundary time crystal, namely in the case in which this cavity loss is large. Then you can adiabatically eliminate parts of the dynamics, the photons in the cavity, and get just a model for the spins which looks exactly modulo the feedback generated terms, which are not super important, as I said at the very beginning, like the equation that I had before. Okay, but still, yeah, one can now ask what happens if I look at this system in the cavity, but not in a regime where I adiabatically eliminate the cavity photons because I have the strong damping, but in a regime where I have somehow, yeah, damping rate that is similar to the interaction rate or even smaller. Yeah. So then you can plot this phase diagram here, so which parameterizes the spin boson coupling. Kappa is the damping rate. So for large kappa, we can do this adiabatic elimination, and then we see very nicely as a function of this laser driving strength, we also have this phase transition here. For instance, along this red line, you see here, we have a stationary phase, and then if we move to the right, we cross a phase transition, and then we are in the time crystal phase. And everything below that is then also in the regime where we can do this adiabatic elimination. We just change the parameter values quantitatively, but qualitatively everything stays the same. Interesting it becomes when the cavity, or when the spin boson coupling strength becomes comparable to the loss. Yeah, then you see suddenly there's something opening here. Yeah, and you see here some kind of wedge that opens up. Here to the left of the wedge, we have a stationary phase. So the yellow signal is just time integrated to even out the bumps. Yeah, so which is more important in the time crystal phase. You see, in the time crystal phase, you have these oscillations, and when you do the time integration, you just go to some stationary state. But what you find in between, this is actually interesting, is you find now that in principle, when the spin boson coupling and the decoherence rate or photon emission rate are comparable, you find a regime of bistability, yeah, or phase coexistence, you could also call it. And I think, okay, you can either look at this plot or you look at this plot. You see very nicely this phase coexistence manifests in the fact that depending on where you start initially, you either end up in a stationary phase. So this is, so to say, this is this red curve here. So let's say here's the initial condition, and then you run towards the stationary fixed point. Or if you happen to be in the basin of the attraction of this limit cycle, yeah, you will run to it and just perform oscillations for eternity. So this is also something that one can probe. So really this kind of ergodicity breaking manifest in this bistable or phase coexistence regime. And then this is almost my last slide. And then beyond the cavities, there has been a nice work by Antoine Brevet. This also links very much to what Tillman said. Maybe this is also something you can do, yeah? Who look at very tightly confined atomic ensembles in free space. Yeah, you see, I mean, you look at ensembles that have transverse width or below a wavelength and just a length on the order of 10 wavelengths. There also you have this, well, weird, let's say, coupling between the atoms and the radiation field, where the atoms lose their individual identity but couple to the radiation, to the electromagnetic field as a collective. And this you can also model with this kind of boundary time crystal master equation that I showed you before, and that you can also get in this atom cavity setting that I showed you before. So this is actually super nice, and they have done some measurements, yeah, which if one wants to believe, maybe show this transition into, we would call it limit cycle phase, they call it differently, that's fine, yeah, or time crystal. The problem so far, and I think this is also really something that is generally a problem when you want to transfer these ideas from theory to experiment, is that the detection rate of photons is very small, and also the current is very small. So there are very few photons only per time recorded or even emitted by an ensemble, because the driving is also weak. So I don't want to overwhelm you with this, yeah, but so the point is now, and we were asking ourselves, what if you could now operate the system really in a regime where you have relatively large photon flux? So is it actually possible, and this links to what I said a couple of minutes back, to now see these different phases in the trajectories, yeah, in the photo output, yeah, either in the photon count or in the photo current that I can detect here in principle at these detectors. And again, as I said, so this model has a phase transition between the stationary phase and this time crystal phase, and now you can have different observables. Yeah? So we are just scanning through here again. Here's the stationary phase, here's the time crystal phase, Here's the critical point. And then the first line is, so to say, theorist's impression. So a theoretician likes to calculate expectation values of magnetizations. So this is an observable relating to the atoms in here. So this is not immediately accessible, right? Of course, you can measure it in principle, but let's say for solving the mass, for theory, it's not difficult to do this. And you see very nicely that you indeed get somehow either a stationary phase or a time crystal phase. And at the critical point, you also find something very funny, which we didn't anticipate. The system is basically stationary for a long time and then has a huge spike. Stationary for a long time and then is a huge spike. And you can also make meaning of this. So by looking at the mean field model plus fluctuations, and it's really funny that also these spikes are distributed, for instance, according to a power law. It's a bit like earthquakes, it's the same. So it's a critical phenomenon. You would also expect this, but this for us was quite curious and has not been seen so far, I think.
So this is without feedback?
This is without feedback, but this is, so to say, what you would, I mean, it's in the same vein because not this, but in principle, the photon count or the homodyne current you could observe with if you wanted to implement feedback. And you see the same structures, I make this short, reflected in the photon count and also the homodyne current here. So at the critical point, these spikes, less pronounced, but you can also filter the signal and you see it a little bit better. But here in the homodyne current, you see this very nicely. You have these spikes and a long time nothing, then spike again. And in the time crystal phase, you see these oscillations. If you were to Fourier transform the signal, it would be clear that there is a peak on the, let's say, expected time crystal frequency. Okay, summary and outlook. So first part, I showed you that we can control this long-range interacting system with feedback and get, so to say, in principle, a squeeze gate for free with a controllable squeezing parameter. Can now ask, okay, how can one use this quantum matter on demand somehow in such an integrated system? There's this quantum enhanced sensing ideas, by Paris and Porras. There's this question, I should have flipped the order here. There's the question of this 1/n scaling, which I mentioned, which they include and get then quantum enhancement, in some way, because you want to have this signal to noise scale in a certain way, and so to say, quantum Fisher information to scale in a certain way. It's a bit cheating, if you start with the equation of motion where the n is already implemented in the start. So this is something to be revisited. Then you can ask, just for instance, Tillmann Esslinger was asking this in his experiments, and Tobias Donner about creation of non-Gaussian states. So far, what we found are Gaussian states. And then also the role of the emission into unguided modes. This is something you have to face eventually. But there you can also, of course, not expect that at stationarity, you will get these perfect phases that I showed you, but there will be a metastable, a transient regime over which you will observe these effects. And then for very long times, these time crystal phase will also not survive. But again, this might be also a bit academic because in practice also experiments are conducted over finite times. Okay, thank you very much for your patience.
Okay, I think we are already quite late.
Yeah.
I think so. If you want to ask him during the coffee break,
That's okay.
which will be shorter because we are already a little bit late. So I think we should reconvene in 20 minutes or something like that.
Das ist dein Segen, glaube ich, ne? Nee? Yeah, thank you. It was a bit much. I wanted to say too many things, but thank you. No, but it's definitely something along your alley of
Yes.
So let's start moving slowly.
Yes. Okay. It should work. Yeah.
Yes, I can change my CPU. The install some I can change that. That's fantastic.
Okay, so let's start again. So the next talk will be of Simeon Mistakidis, and he will be talking about dipolar BECs with rotation.
Yeah, thank you very much for the kind introduction, and let me again thank all the speakers for the very nice talks up to now, and of course all the participants. So today I will talk about two separate stories. The first one will be about the phase diagram and the dynamics of dipolar Bose-Einstein condensates subjected to a fastly rotating magnetic field. And then I will switch a little bit gears, and I will not discuss long-range interactions, but still magnetic atoms. And I will discuss in particular the classification of universal dynamics in spin 1 strongly interacting ferromagnetic condensates. So our work on dipolar gas is available in Physical Review Research, and before I start my presentation, let me also thank NSF for funding our research here at ITAMP. Okay, so this brings me to the outlook of my talk. First, I will provide a very brief introduction into the concept of dipolar Bose-Einstein condensates. I don't have to do more than that, because all the experts are here. Then I will discuss the phase diagram and the spontaneous generation of droplet clusters upon consequences of the S-wave interactions. And finally, in this story, I will try to convince you and argue that using this fastly rotating magnetic field, we can, to a certain extent, achieve some prolongation of lifetime of these self-bound states. And then, as I said, I will switch a little bit gears and discuss a little bit the classification of the universal dynamics in spin 1 gases. Okay, so dipolar quantum gases consist commonly in the experiment either by dysprosium, erbium, or very recently by europium atoms. These atoms have very large magnetic moment, and under, as you see here, for an elongated gas, under the impact of an external magnetic field, they can be aligned. And then we can distinguish roughly two different situations. Either the dipoles can be aligned to an external magnetic field. Our unit R is the unit vector here of the dipoles. Ez is the unit vector of the external magnetic field. If they are aligned parallel, then this will lead to a head-to-tail arrangement, and the dipoles will attract each other. And on the opposite case, where they align perpendicular to the external magnetic field, this will lead to a head-to-tail, to a side-by-side distribution, and the dipoles will be repulsive. So, It is in these gases the interplay between long-range anisotropic dipole-dipole interactions and short-range S-wave ones that lead to various many-body phases of matter, and these include, for instance, anisotropic superfluidity or the generation and formation of exotic bound states of matter like quantum droplets and supersolids that we will discuss today. So, for instance, here you see in the left, in the most left-right panels, the density distribution, a characteristic density distribution of a droplet lattice in two-dimensional geometry and a supersolid. In the droplet, you see that we have well-localized density hubs that are almost non-communicative between each other, while in the supersolid we have an accumulation of density bumps on top of a superfluid that are weakly linked, these bumps, by this superfluid, by the background superfluid, and this leads to the supersolid, roughly, pictorially, state of matter. These states have been observed recently in a series of experiments, and especially the supersolid is believed up to now that it combines essentially the superfluid frictionless flow, and it has simultaneously the crystal arrangement of a solid. Okay. So in these gases, the really nice thing is that there is an unstable eigenmode, the so-called Rotten mode. You see characteristic special profiles of this mode of the lower line and the few first excited ones here, and also the dispersion relation of this dipolar gas. So for strong repulsive dipole, for strong attractive dipole-dipole interactions, we have this Rotten softening, and then this leads the dipolar gas to collapse. However, here, if we include quantum fluctuations into our gas, and these are commonly modeled by the first-order Li-Huan-Yang quantum correction, they act repulsively in 3 dimensions, and in particular as n to 3/2. They stabilize the gas and they lead to formation of these exotic phases of matter. And if under these first-order correction, we can have theoretical concepts like the extended Korspitevsky that I will also use here in this work in order to describe the static and the dynamic properties of the systems. And this concept, this framework, has been shown to very nicely describe also experimental observations. Okay, so here what I will do is to use a fastly rotating magnetic field in order essentially to tune the dipole-dipole interactions, both the magnitude and their sign, and I will try to show you the impact of this anisotropy on the self-bound state formation and how we can really shift the phase boundaries between the exotic phases of matter. And also I will discuss a little bit metastable states that arise during the dynamics and how we can dynamically nucleate these states. Okay. So this will be the setup under consideration. It will be a quasi-two-dimensional dipolar gas of dysprosium atoms in the XY plane. And we have an external magnetic field that is tilted with respect to the z-axis with a tilt angle phi. And this will be really fastly rotating. Why is that? So first of all, the dipoles will be aligned along this unit vector. This unit vector E of t will contain the tilt angle, but also the angular frequency of the external magnetic field. And this angular frequency will be chosen such that it is much larger than the external trap frequency, but much smaller than the Larmor precision frequency of the dipoles. In this way, the dipoles will essentially instantaneously follow the field rotation. Okay, so since I will consider a fastly rotating magnetic field, it will be completely legitimate that what I will do is to consider essentially a time average version of the dipole-dipole interaction potential over a full rotation cycle. And if I do that, then I will end up with this interaction potential, dipole-dipole interaction potential. It has the r to the cube dependence in the denominator, so it is long range, and also this direct product between the unit vector of the magnetic field and the dipoles in the denominator, and that's why it is anisotropic. So here what we have to observe is that there is a magic angle, phi m, at which the dipole-dipole interaction potential vanishes. then we have just short-range interactions into our system, so we will have only superfluid states to care about. However, we can tune this tilt angle, and in particular, if we tune this tilt angle and increase its magnitude, but lying below the magic one, then we can think that in the xy plane, we will increase the, we will decrease the magnitude of the dipole-dipole interaction, and the dipoles will be repulsive. In the opposite case, where we will further increase the tilt angle, but above the magic one, then the dipole interaction will flip sign, so it will become attractive. And as I increase its magnitude, then also I will increase, as I will increase the tilt angle, also the magnitude of the dipole-dipole interaction potential will increase. Okay. So, in order to describe the ground state properties and the dynamics of the system, what I will do is to rely on this three-dimensional extended Krosp-Pitayevsky equation. What it has is that the first term is the kinetic term, the second term is the three-dimensional harmonic trap that I will consider, the third term has the S-wave interactions, the fourth one is the first-order quantum correction, the Li-Huang-Yang, and the last term is just the anisotropic dipole-dipole interaction potential. Okay. In particular, I will consider these trap frequencies taken from the experiment, and I will use for my description these prosium atoms having this magnetic moment and this dipolar length. And what I will do now is to consider variations of the relative interaction between the dipole-dipole interaction and the S-wave one. And this is quantified by this epsilon d parameter. Okay? So, what you see here is the phase diagram in the case that I have an aligned magnetic field in the z direction. So, no rotation, very simple static field in the z direction. So what you see here is the phase diagram in terms of the particle number and also this relative interaction strength parameter. And in the color bar, what you see is the chemical potential of the system. Okay. So for relatively small, the relative interaction strength, what we will have is a superfluid state, simply because the S-wave interactions will dominate with respect to the dipole-dipole ones. Then as I increase this relative strength parameter, and in particular, when the dipole-dipole interaction becomes comparable to the S-wave one, and in the vicinity of the zero chemical potential that is shown here with the dashed white line, I will have, for large particle numbers, the formation of a supersolid. If I further increase the relative interaction strength, then the dipole-dipole interactions will prevail, and I will have, depending on the particle number, either a single droplet or multiple droplet state, this DLS and DLM that you see here. Okay? So, in order to visualize all these phases that I described below, here what I show you is the two-dimensional densities in the XY plane for different relative interaction strength parameters. So, in the first one, where the relative interaction strength is relatively small, we have a nicely smooth two-dimensional Thomas Fermi profile. This is just the superfluid that we all know. Then, if I increase the relative strength between the dipole-dipole and the S-wave ones, then humps will start to accumulate on top of the background superfluid. They will be weakly linked by this, and I will have this characteristic profile of a supersolid. And if I further increase this relative strength parameter, the dipole-dipole will prevail, and all these density bumps will strongly localize in space. They will not communicate between each other, and here I have, due to energy considerations, just a hexagonal droplet lattice. Okay? Then, up to now we discussed the phase diagram in the case of a static magnetic field, but now what will happen when we consider the rotation? So here what you see is three different characteristic phase diagrams. In the first one, with a static magnetic field. In the second, I have a finite tilt angle, but below the magic one. And in the third, an even larger tilt angle, but above the magic one. Okay, so if I compare now the first and the second plots here, what I will see is that the supersolid region shrinks. The same happens for the droplet, and all of them are shifted towards larger relative strength interactions. Yeah? This is simply because when I increase the tilt angle and being up, below the magic one, what I do effectively is to decrease the magnitude of the dipole-dipole interactions. Then, if I increase further the tilt angle, but above the magic one, the dipole-dipole interaction flips sign, it becomes strongly attractive, and here in this so-called anti-dipolar regime, what I will have ultimately is just the formation of a superfluid or a single droplet phase. Yeah? Due to the strong, sure.
About the LHY correction.
Yes.
If you have this time averaging, how do you treat the LHY correction? Do you assume that it's like this epsilon that you are plotting here, or is it a time averaged epsilon, or what?
This is a time average epsilon, yes.
Okay, and I mean, if you flip the sign, for example, you are also flipping the sign of the
what, LHY?
of the LHY, or?
Yes, so the LHY that I consider is this one. Yeah?
So yeah. Okay, but okay, so then you.
So this rotation is really fast. So if, for instance, in the simulations, either I instantaneously follow the magnetic field or I do the time average for the dipolar potential, I get the same result. Yeah? It's so fast. So it's at least 300 times the trap frequency. If I go below, then defects will start to be created in my density, and then this approximation will not be valid anymore at all. But this is a different regime. Yeah. Okay. So, yes. And in the attractive dipole-dipole interaction, I will end up with a superfluid or a single droplet phase. Okay. So now what I will do is also to start to try to dynamically nucleate these phases. And to do so, what I will do is to start with the initial superfluid phase, yeah, and just consider an S-wave, a quench of the S-wave interaction towards either the droplet or the supersolid regime. Now I will show you just the droplet regime, but the same will occur also for the supersolid. Okay? So when I quench the S-wave interaction and I go from the superfluid to the droplet regime, what I do effectively is to seed the corresponding Roton instability that we talked about previously. This will lead to a dynamical deformation of my state and will nucleate, as we will see, these droplet lattices. So here what you see is characteristic density snapshots of quasi-two-dimensional dipolar Bose-Einstein condensate starting from a superfluid state. So initially you see that we have a nicely formed, smooth Thomas Fermi two-dimensional profile. Then as time evolves, ring-like structures start to accumulate in the density. These manifest that lower line Roton modes participate in the dynamics. They subsequently fragment one after each other because higher line Rotons participate, and then we have the nucleation of a droplet lattice. This is quite disordered because we have used also an external noise in our wave function during the quench. Okay, so what I said up to now was for sure for a closed system. However, in the experiments, there are also significant three-body recombination processes that lead to loss processes in the system, and I want to show you now that even by including these three-body recombination processes, we can see the generation, the dynamical generation of these structures. And also, the most important thing here is that by using this fastly rotating magnetic field, we can achieve a certain lifetime prolongation of these self-bound states. So what I will do in order to monitor the dynamics is I will use again the previous three-dimensional Krosp-Pitevsky equation, but I will use also this last imaginary term here, which scales with this K3 coefficient, which is the recombination rate and the density square. The important property here is that we know from scattering theory that since if we use this tilted magnetic field, this fastly tilted magnetic field, we can distinguish between two different situations of the three-body recombination rate, depending on the comparison between the S-wave interaction and the dipolar length. So the three-body recombination can scale either as d to the 4 or as to the 4. And I will show you now that in the crossover between these two regions, we can achieve a certain lifetime prolongation. Here is what you see here, which depicts the dynamics of the atom number as during the evolution for a specific epsilon dd parameter. So I fixed my relative interaction strength to the droplet phase. And what I do for the different colors here is to change the tilt angle, yeah? But lying always below the magic one. So what you see here is that as we increase the tilt angle, we can achieve a certain extent of lifetime prolongation of the droplet. Okay? And of course, at the small evolution times, sorry, I forgot to say that, we can also see the nucleation of droplet lattices. The same happens for the supersolid, and the same results holds also in the quasi-1D geometry, both for the static and the dynamical properties. Okay, so now I would like to switch a little bit gears and discuss a little bit the classification of the universal dynamics in a strongly ferromagnetic spin-1 Bose-Einstein condensate. Our work also is available in archive here. Okay. So, let me say a few things about spinor gases. So, spinor gases are not long-range interacting. We have only short-range interactions here, but we have magnetism. Yeah? So, these gases are known pretty well up to now that they can host a plethora of quantum phase transitions, both first and second order. These gases are characterized by spin-dependent and spin-independent interactions. This C1 coefficient is the spin-dependent interaction that you see here. For sodium-23 is positive, for rubidium-87 is negative. Yeah? And according to this, we can realize different first and second order transitions. With the dashed green lines here, you see the boundaries of second order transitions, and with the red ones, you see here, you see the boundaries of first order transitions. Okay, so these phase diagrams are plotted with respect to the quadratic Zeeman energy coefficient and the linear one. Yeah. However, up to now, what it has been used in the literature is either sodium-23 or rubidium-87, and the main disadvantage of these two gases is that they have weak spin-dependent interactions compared to the spin-independent ones. In particular, sodium-23 has a ratio of roughly 1.5% and rubidium-87, 0.5. Yeah? However, these gases has been used vastly in the literature and have diverse applications to understand spin textures, nonlinear excitations, vortex structures, testifying the Kibble-Zurek mechanism, and so on. And very recently, they have been used also to diagnose dynamical criticality and measure critical exponents. A major obstacle, of course, up to now was the weak spin-dependent interactions compared to the spin-independent ones that essentially prevented to monitor these gases for long evolution times, in the experiment at least. Here, what I will show you is that using lithium-7 gas, which is strongly ferromagnetic, yeah, it has 45%, so it's an order of magnitude larger than the other ones. This will allow us to classify the universality class of the underlying phase transitions and also monitor the evolution of the gas for long evolution times. Yeah? And see also the create topological defects. So what we will do is to have, and this is a work in collaboration with the experiment. Yeah? Okay. So what we do here is to have a quasi-two-dimensional spin-1b. See, with this number of atoms, this is the frequencies of our external trap. And we will initialize all atoms in the so-called polar phase here, which means that all atoms initially will lie only in the zero hyperfine level. So I forgot, sorry for that, I forgot to mention that these spin-1 gases under the external magnetic field, we can split to 3 different hyperfine levels, plus, minus 1, and 0. And here I will start with a quadratic Zeeman energy coefficient that lies in the polar phase, and I will populate only the 0 hyperfine level. And then what I will do is to quench this quadratic Zeeman either to the so-called easy axis phase, where in the ground state I should see population only of the plus minus 1 hyperfine levels, or to the isotropic point where all states should be populated. For reasons of time, I will just talk about the easy axis quench here, but similar results, maybe even more complex, will hold also for the isotropic phase. Okay, so the initial phase, as we said, is the 0 phase. Only the 0 hyperfine level is populated, and we will quench to the easy axis where in the ground state, plus minus 1 states are populated, and this state has also U1 cross Z2 spin inversion symmetry. Okay? Okay, so to tackle theoretically this problem, I will use this 3-dimensional coupled set of mean field equations of motion. Yeah? This is the kinetic term, this is the external 3-dimensional trap, this is the quadratic Zeeman coefficient, Fz here is the spin Pauli matrices, C0 here models the spin independent nonlinearity, and C1 the spin dependent one. What I will do is to first initialize my system in the mean field ground state of the polar phase with a specific quadratic Zeeman, so only the 0 component will be populated. And then what I will do is to use a linearization. I will linearize my solution around my mean field solution, which is the polar phase, and perturbed by a weak amplitude here, epsilon, and the eigenmodes and eigenvectors of the system. Eigenmodes and eigenfrequencies of the system, sorry. Okay, so in order to calculate this, I solve this eigenvalue problem, I determine my eigenvalues and eigenfrequencies, and I use this noise field, which is a superposition of the corresponding U eigenmodes and betas, which are random values that are chosen for the plus minus 1 level from a Gaussian distribution with unit variance and unit mean, and also for the 0 hyperfine level, I will use the Boltzmann distribution. Of course, this choice to use quantum fluctuations in the plus minus 1 channels and 0 in the and thermal fluctuations in the 0 hyperfine level is motivated by the experimental observations. Okay. So I prepare my state, my system in the polar phase. I do a quench to the easy axis, and here is the spin populations during the evolution of the different hyperfine levels. So initially, as you see, everything is in the 0 hyperfine level. And here we can distinguish different dynamical stages of this evolution. For short evolution times, we have an almost exponential increase of the plus minus 1 populations, yeah, and an exponential decrease of the 0. This, as I will argue now in the next slide, it will be associated with the formation of topological defects, which in this case are gauge vortices. Yeah? Then these vortices will start, and anti-vortices will start to interact and annihilate or drift out of the condensate, and this will lead to the formation of magnetic domains. And these magnetic domains, after forming, they will start to merge, and finally I will enter the so-called coarsening stage where my gas has universal properties. Okay. So in order to show you the different dynamical stages here, what you see is the two characteristic density snapshots during the evolution in the upper panels of the plus 1 component, in the lower panels of the minus 1 component. Yeah? The 0 I don't show because essentially the 0, although it has initially full population of all atoms, then it just loses it. Okay. So what we see here is that initially, for short evolution times, we have the creation of gauge vortices and anti-vortices in the system, which you can see here by the dips in the density. Then these interact and annihilate or drift out of the condensate. They give rise to magnetic domains, and these magnetic domains start to increase essentially their length, and at the end of the evolution, I end up with a single domain well between the plus minus 1 components. Okay. So in order to convince you that these dips that I told you before are vortices, what I show you here is essentially the wave function phase of the minus 1 component, where you see with these crosses the 2 pi phase windings that identify the vortex structures. Okay? While in the long time evolution, where I have just a single domain, well, you see that there is no such phase jump. Okay. Then, in order to see the interplay of the different effects during the evolution, what I do here is to measure, first of all, the number of vortices during the evolution. This is shown by the dashed lines here, and also the specially resolved magnetization, which quantifies the number of magnetic domains that I create in the system. So what we see here is that initially we have an almost exponential increase of vortices. Then, through their interaction, as we said before, they annihilate and their number starts to decrease. And complementary to it, magnetic domains start to be created in the system. The magnetization increases, it oscillates, and it oscillates because we have an external harmonic trap in the system. And this external harmonic trap, after the quench of the quadratic Zeeman coefficient, leads to a background breathing motion, so a collective compression and extraction of the system. Yeah? And this causes essentially the oscillatory behavior of the magnetization. If I didn't have the trap, then all these oscillations will be suppressed, and I will just have a straight line. Yeah? Okay. So then, in order to argue about the universality of my system, what I will do is also to track the correlation function of the longitudinal magnetization. And this is what is shown here for different evolution times. All these are experimental data here, all these circles at different evolution times that you see in the color bar. So what we see is that the correlation function decreases for increasing distance. It crosses 0, and this 0 is the average domain length. And if now if I rescale my correlation function with these individual domain sizes, what I will get is that all correlation functions for different time instants will fall on top of each other, so they exhibit a self-similar behavior, and then we have a universal behavior of the gas. The circles here indicate the experimental data, and the solid line is our theory prediction, which are in quite good agreement. Okay. Then, in order to identify the critical exponent, what I will do is also to monitor the average domain size during the evolution, which is naturally increases, as we saw also from the densities. So here, this plot shows during the evolution time the average domain size. Again, the circles indicate the experimental data, and the solid line indicates our theory prediction, while the dashed one is just the fit in order to identify the critical exponent. And here we have identified 0.61, the critical exponent in the experiment, and 0.59 in the theory. This small deviation that we see between the theory and experimental observation is attributed to the finite resolution of the magnetic domains in the experiment, which they have like 2 micrometers, but in the theory we have seen that there are domains even of smaller size. And another important thing here is that the thermodynamic limit prediction is 2.3. So both in theory and experiment, we see deviations from the thermodynamic limit. And this is now attributed to finite size effects that are introduced from our external trap. Indeed, we have verified, first of all, that the critical exponent takes some corrections from the spin healing length of the condensate. And also, we have verified that if we go to the thermodynamic limit by either increasing our particle number of the order of 10 to the 8 or going to the homogeneous case, we will retrieve the thermodynamic limit prediction. Okay, and since in the easy axis phase the spin 1 gas behaves as a binary superfluid, this the universal dynamics essentially belongs to the binary universality class in this case. Yeah? Similar arguments could hold also for the isotropic quench. There we have a different phenomenology and different universality class and different topological defects, which are their spin vortices, but I will not discuss them today. Okay, and finally, what I would like also to say is that, okay, I told you that this is a universal dynamics, but this I have to prove, right? So, in order to prove that, we have also taken different initial conditions. Here I show you just 3 from the experiment, in order to use a different initial condition and see whether first the critical exponents change and whether we observe the universal dynamics. So here what you see is essentially 3 different initializations of the system, always being initially in the polar phase, but in the first experiment we use a field gradient to populate the ±1 states, and then we quench again to the easy axis. In the second experiment we imprint in the again in the polar phase where all atoms populate the 0-state vortices in order to see whether the imprint of topological defects will change the exponent and the dynamics. And in the third one, what we do is essentially to be again in the polar phase, but in a different quadratic Zeeman coefficient, and then do again the quench. In all these cases, we show here the corresponding correlation function. You see the data for all these different cases. They fall on top of each other. And this has been confirmed both by theory and experiment. Okay, and we have measured the same critical exponent. Okay, with this, I would like to thank all of the individual collaborators that have participated in the individual works, in particular also very much the experimental group of Ye-Yun Choi, Hussein from here, Panos Kevrakidis from University of Massachusetts, Kushik Mukherjee from Lund University, and the other collaborators from India. So with this, I would like to thank you so much for your attention.
Thank you very much. Questions? Yes.
So when you tune your dipoles to be attractive by rotating them over, what's the conditions for it to be quasi-2D in that case?
Sorry, you mean in the dipolar case?
Yeah, in the dipolar case. So when you're rotating them tilted to 90 degrees, are the conditions quite strict to be quasi-2D now because it won't want to collapse in the vertical direction?
So the trap frequencies that we have used, sorry. So this is the trap frequencies that we have used for the quasi-2D geometry. And as I said, the the angular frequency of the rotating magnetic field, it should be at least 300 times larger than the trap frequency, but much smaller than the Larmor precision frequency. This is the condition.
So you're assuming it's in the ground state in the Z direction there?
Yes.
But won't when it...
So in the Z direction, we didn't see too many excitations during the evolution.
So I'm just wondering if it's become attractive in that direction, won't it want to collapse?
Yeah, it becomes really highly elongated in this case.
But now you have inverted. You're talking about the inverted.
Yep.
Yes. So in the anti-dipolarism, you mean, right?
Yes, it's really an anti-dipolar.
So in this case, we see really a very highly elongated, I can show you the profiles afterward, across the Z direction, if this is what you ask. Is this what you ask?
I thought it would have gone very flat, disc-shaped for droplets.
If you put it anti-dipolar, then it's attractive in the plane and repulsive here, so it must become flat. It can become elongated.
I guess this is correct. Yes, sure. Yes. Correct, yeah.
So I guess my question is just, is the quasi-2D approximation going to be appropriate there? Won't the system try to violate that approximation?
Why should violate the approximation?
Because it's attractive in that direction, so it's going to, just like when they're tuned, in the normal way when you don't tune them, the droplets become very filament-like, so they naturally attain a size that's not set by the confinement.
Yeah, this I have to think about it. Maybe, yeah. But I can show you some profiles then and we can discuss. Yeah, sorry.
Any other question? Yes, please.
It's just a practical question
Yes.
about the prolongation of the lifetime that you showed with the K3 coefficients. So, I mean, when you did this final estimate, this one here, you fixed the epsilon.
Yes, I fixed the epsilon to
But
be in
of
the
course, if you
droplet.
fix the epsilon with tilting the angle, you have to change the scattering length as well, and then the K3 is changing.
Yes.
So, did you assume a constant K3 here?
No. The K3 scales as d to the 4. So I change essentially this, right? The dipolar length.
So you are in this regime where epsilon dd is sort of much larger than
Yes.
1. Yeah.
Yeah.
Okay. Okay. It's 2. Okay. But in practice, I mean, if you do this, let's say in this parameter regime, I would say that the K3 is.
We have done the same for close to unity for the super solid, and we observe similar things.
Okay. Thank you.
Yes, please.
What is the typical trap frequency you're using in this simulation for this process?
This one. 45 here. 133.
Okay. So it means that the rotating frequency would be like 30 kilohertz.
At least 300 times larger than 45.
Okay.
At least.
Okay, thanks.
Okay. Any other question? So if not, thank you again.
Thank you.
So the next speaker is Elena Poli from Innsbruck, and she will tell us something about rotating dipoles, rotating dipolar quantum gases.
Is there the pointer, or do you have the? It was. Yeah, thank you. Sorry. Okay, sorry. Great. So, good afternoon, everybody. My name is Elena Poli, and I'm a PhD student of the theory group of Francesca Ferlaino in Innsbruck. Before starting, I would really like to thank the organizer for giving me this opportunity to be here at ITAMP, representing my group together with my colleagues. So today we already had a lot of talks talking about dipolar gases. From my side, I will try to give an update about our latest results in Innsbruck. Sorry. Okay, it's worked. Sorry. In my group, we work with atoms like erbium and dysprosium that have a large magnetic moment. And so, in addition to the tunable contact interaction, these atoms also interact via the long-range and anisotropic dipole-dipole interaction. And the possibility to tune the S-wave scattering length by means of Feshbach resonances experimentally allow us to, to balance the interplay between these two different interactions. And so we can basically work in different regimes that could be contact-dominated or dipolar-dominated. And in particular, in this dipolar-dominated regime, this is the regime in which we can access the supersolid phase of matter. So I will structure my talk in the following way. First, I will recap a bit the results from my group about supersolidity, in particular focusing on the structural phase transition from 1D to 2D supersolids. Then I will talk about dipolar gases under rotations. And finally, I will give an update about the possible applications of rotating dipolar supersolids. And in particular, I will show how this system could actually tell us something about a phenomenon that is the glitches that usually happens in neutron stars. So let's start with the first part. This is let's say, there already have been a lot of talks about supersolidity, so I will try to summarize a bit the main properties of this state. So here there's a nice experimental in situ image from our erbium dysprosium lab, in which you can see that basically this is a 1D supersolid. With this, I mean that the system is actually 3D, but it spontaneously breaks the translational symmetry in one dimension, in this direction, and forming these nice 6 droplets. And these droplets are not independent between each other, but they actually share a global phase coherence that can be experimentally detected by studying the interference pattern. So you let your system expand with a time of flight measurement, and you can actually prove that the system share the droplets share a global phase coherence. We know that the origin of this state comes from the softening of the Roton mode in the excitation spectrum of a dipolar Bose-Einstein condensate with a tight confinement along the Z direction, as it was predicted back in 2003, and as it was also experimentally observed in 2018 and 19. And so by tuning the interaction, when the Roton minimum completely softens, and so when the Roton gap goes to 0, the system does not undergo a collapse as it was predicted, as it is predicted by a mean field theory, but it is stabilized by quantum fluctuations that in the theory we can take into account by considering the first beyond mean field effect that is given by this term, that is the Lee-Wang-Yang term. That is repulsive, it is isotropic, and it rapidly scales with the density, and that's why it becomes important when there are these high density regions formed that are the droplets. We know that this state is robust against phase scrambling because it kind of activates a rephasing process quite quickly, reestablishing the global phase coherence. And this process can be modeled by a Josephson array model. And we can also, we also know how to produce this state, in particular via 2 different methods. Either by interaction quench, so by basically lowering the scattering length by means of Feshbach resonances, or by directly evaporating into the supersolid state. This, let's say, the first experimental observation of 1D supersolid was back in 2019 by 3 groups in Pisa, in Stuttgart, and in Innsbruck. And so then the question was like, how scalable is this system? Because the first supersolid was in 1 dimension, so how scalable is this system? So the first intuitive way to scale the system from a 1D chain to something that has a 2-dimensional structure is to release the trap confinement along the transverse direction, such that the system can develop a transverse structure. And we performed some numerical simulation with the Gross-Pitayevsky equation, And we found out that we realized that if you just release your transverse confinement and you leave all the other parameters constant, actually at a certain point you lose the super solidity and you fall again into the BEC regime. If instead, in addition to releasing the transverse confinement, you also load more atoms inside the traps, you also increase the atom number, and in particular, if you keep constant this parameter here, that is a measure of a trap density, so if you keep constant the density of atoms inside your trap, like you manage to maintain the super solidity crossing the 1D through 2D structural phase transition and eventually end up with this nice state with 19 droplets in a circular trap. So this is what we also try to do in the experiment. Basically, by increasing the trap aspect ratio, we observed also an increased atomic aspect ratio in correspondence of the point in which the system starts to develop also a transverse modulation in the transverse direction. And so we could range from a linear chain of droplets to something that is more zigzag or more complex, like this double zigzag, up to basically this nice hexagonal state that is in an almost circular trap. And of course, we can always, as I said at the beginning, we can always check that all the droplets share the global phase coherence by performing time of flight measurement and always benchmarking with the theory obtained for the same parameters of the experiment. So at the moment, I always talk about density modulation and global phase coherence, but another property that we expect from this kind of state is like superfluid properties. And so in particular, we would like to verify directly these superfluid properties by means of the observation of quantized vortices that would be a direct manifestation of the superfluid nature of the system. So the open question we had is, how can vortices nucleate in a dipolar system? And this was an open question not only for this nice super solid state, but also for simply a dipolar BEC. And so to study this question, to try to answer this question, we decided to take a step back and study rotations first in the non-modulated regime. So this opens the second part of my talk, in which I will introduce how can we actually rotate this kind of system. So if we have a rotating bucket that is rotating with a certain angular frequency omega, and we put a normal fluid inside of it, at equilibrium, this fluid will just rotate together with the bucket. If instead we put a superfluid and we rotate the bucket, let's say, under a certain critical value, we would see that this superfluid, if the bucket is cylindrically symmetric, this superfluid would not rotate at all. And if we increase the angular frequency up to above a certain critical value, we will see that the system will develop some topological defects inside that are called quantum vortices. And the number of vortices is proportional to the angular frequency of the system. So if we have a closer look on one of these objects, we will see that these quantum vortices corresponds to, they manifest as density holes that are characterized by a 2π phase winding around the central point. And the size of the core of this object in general depends on the chemical potential. And if we compute the circulation of the velocity around the vortex, it is quantized. So we would like to obtain a state like this in our dipolar system. So the question is now, how can we actually reach this kind of state? So in the last few decades, a lot of experimental techniques were implemented to create vortices inside systems. The first, maybe intuitive way is really to induce a rotation to the system, for example, rotating a slightly anisotropic trap, and so inducing a rotation to the system that can develop these holes in the middle that are the quantized vortices. Or you can, for example, put a mechanical perturbation to the system, for example, steering an obstacle, and this would create some phase fluctuations that will create some vortices inside. Another technique is, for example, a rapid cooling across the phase transition from a normal to a superfluid state. Or we can also, in principle, one can also directly imprint a phase pattern on your system by using a DMD. And all these techniques were used for Bose-Einstein condensate with only contact interaction. But as I said at the beginning, in our condensate, we also have dipole-dipole interaction. And so we decided to exploit this property of the system to induce a rotation to it. In particular, by using this method that we called magnetosteering. So if we had like a system, like a non-dipolar system in a trap, basically the shape of the cloud would match exactly the one of the trap. If instead we have a dipolar system, and so for example with a magnetic field that is pointing, for example, in the z direction, because of the dipole interaction, also the cloud would stretch in the same direction of the magnetic field. And this phenomenon is called magnetostriction, and it was seen in 2007 in the group of Tillman-Pfau. And basically, it's just a consequence of the fact that since we have dipoles, they favor configuration in which they are head to tail. But this means that if now we tilt the magnetic field, these dipoles would like to align along the direction of the magnetic field, let's say breaking the cylindrical symmetry of the system that was before because of the trap. And so if we then start rotating the magnetic field, the system would follow it. And so we can induce a rotation and we can impart angular momentum to the system by rotating the magnetic field. And this can be done in the experiment by using 3 pairs of coils that can, each one of them is responsible for the magnitude of the magnetic field in each of the 3 directions. If you want to have a classical analog, this is also what happens, for example, if you have a ferrofluid and if you want to rotate it with using a magnet, you will see that these droplets are aligned in the direction of the magnetic field, and if you rotate the magnetic field, they will just follow it. So we expect that this method would impart angular momentum to the system. And in particular, what we expect is that for increasing values of the rotation frequency, the system would elongate more during the rotation until it reaches a dynamical instability at a certain frequency. And this dynamical instability is the seed for vortex nucleation. So it's the seed to have vortices inside the system. So to study this, we first decided to do some simulation to understand which were the best experimental conditions to observe this. And in particular, we decided to study the stability of the system, since we want to see when the system becomes unstable and when we have vortex nucleation. So we studied the stability of the state depending on the tilt angle of the magnetic field, the initial tilt angle. What we observed is that for small values of this tilt angle, from 0 to 20 degrees, the aspect ratio of the system increases not so much, and then basically it goes back to 1. So we don't observe, so this is like the state at the beginning and this is the state at the end, and we don't basically observe any vortex in the middle. For intermediate values of this angle, actually, we see that the aspect ratio of the system increases. It reaches a maximum, and after that, it basically collapses again. So this is the moment in which the system undergoes the dynamical instability, and after that, we have vortex nucleation. You can see that there are holes in the middle of the system. If we increase even more the tilt angle, basically we are the attractive dipolar interaction of the atoms that now are even more head to tail is so strong that it suppresses the dynamical instability. And so you see that the aspect ratio keeps increasing, but it does not collapse. So from this analysis, it's quite clear that this middle range is the best one for the experimental, to observe this dynamical instability and this vortex nucleation experimentally. Here you can see that these are some experimental points obtained for this specific value of the angle. That is the one that we used for the next results that I will show. And in order to optimize the time for vortex nucleation in the experiment, we decided to rotate the system at a frequency close to the value of the dynamical instability. So without doing this ramp, we just set the frequency of rotation at this fixed value. What we expect is something like this. So here there's a simulation in which we tilt the magnetic field and we start rotating at a constant frequency that is something like this. So first you see that the dipolar BC gets elongated as expected. Then it's spiralized somehow. And here you can already see that, so first there are some quadrupolar deformations at the beginning. And then you see these holes, and so these vortices in the external low density region. So they are created and they slowly start to enter inside the system. Here you can see that the vortices are trying to go inside. And this is the moment in which the aspect ratio of the system that first was really elongated, it basically goes back to 1. Okay. So this is a simulation, and here there's the comparison between simulation. Basically, these are just some frames of the previous simulation that I show with the experiment, and you can see that there's a good agreement for the same time scales. So first there's this spiral, and then you can see that there are vortices, and vortices enter, and the same you can see here. Here there's the spiral with some. Then start to see these holes, and these holes go basically inside the system. In experiment, we have atom losses during the rotation, and so that's why the size of the cloud is smaller, in particular at the end, compared to the one of the simulation. So one peculiarity, so there are some peculiarities for vortices in dipolar systems. In particular, when the magnetic field is in plane, we expect the vortices to have an elliptical vortex core, just because of the dipole-dipole interaction. We also expect that around the core of the vortex to have some density ripples, in particular if we are close to the if we are close to the Roton instability point, and then, in particular, we also expect to have an altered vortex lattice. So instead of the triangular lattice that we have in contact-dominated BC, we expect to have this stripes configuration. So the vortice is aligned in stripes instead of a triangular configuration. And in particular, we focused on this last property. And what we observed is that this is the ground state of the system in the rotating frame for the same parameters of the experiment. So when the magnetic field is in plane, so it's still tilted. And these are some experimental results, and these are the simulations for the same time scale. And so if you plot the residuals that are obtained by subtracting to the density, the blurred density, in order to see a bit better, and we use this method to detect the position of vortices. So you can see that these vortices are kind of aligned. They have this preferential direction that is more visible if you perform a Fourier transform of the residual, because you see the presence of these two peaks in the K-space that resembles the periodicity in stripes in the space, in the position space, or in the residual. If you then tilt the magnetic field in the Z direction, again, you lose this feature because you basically restore an isotropic vortex distribution, like that you can see here in these two cases. So again, experiment and simulation. And this is quite clear if you perform the Fourier transform, again, of the residual, in which you see this ring that really resembles that now you don't have any preferential direction anymore. So all these results were obtained for Bose for the non-modulated state. But as I said at the beginning, we would like to extend these results also to the supersolid state. And so in the theory, in particular, we would like really to apply the same protocol to just a state that is obtained by lowering the scattering length. And so in particular, we would like to tilt again the magnetic field and rotate it so as it is in this simulation. So we expect the droplets to follow the rotation, and so we are inducing a rotation to the system, and as you can see from the phase, here at the end, after a certain amount of time, there are, for example, here 2 vortices. And one important thing is that the critical frequency for to have vortex nucleation is expected to be lower than the one that we have in the BC, because the energy barrier that the vortex has to overcome in order to be inside the system is lower because of the lower density region in between the droplets. And so, notice that here the frequency is, before it was 0.75, it's 0.25. So here there are some experimental results in which you can see that by tilting the angle, we are actually also tilting the droplets that align along the magnetic field direction. And here you can see that if you rotate the magnetic field, also the droplets would follow it. So we managed to rotate a supersolid state with the same protocol that I showed you before. Now there are 2 main challenges. The first one is that when you produce vortices inside the system, they will stay in the low density region in between the droplets. And so the question is, how can we actually detect them? And second, is the lifetime of the supersolid, in particular during the rotation, long enough to observe a vortex nucleation? So to try to answer this question, we follow this theoretical proposal from the group of Stringari in Trento. And so in particular, they say that if you manage to produce a vortex in a supersolid state, and then if you quench the scattering length in order to cross the supersolid to BC phase transition, this vortex should remain, so if you have a vortex here, the vortex should remain inside the system. And once you are in the BC regime, you are able to detect it, as I showed you before. So here there are some preliminary results that we obtained very recently, in which you can see, so this is the protocol that we applied. So basically, we rotate a supersolid in the way I showed in the previous slide at this value of the frequency. Then we spiral up the magnetic field, and we perform this quench into the BEC regime. And what you can see is that you see that the system has a null in the middle. This is for 3 different time interval of rotation. So this is obtained for different time. But the result is the same. If instead we apply basically the same protocol, but rotating at the same frequency, but in the BEC regime, so we do not observe any vortex nucleation. So because this omega is too low to produce a vortex nucleation for the same time scale. So these are really preliminary results. We are still producing these, and we are still analyzing what we have. But it seems that very, very promising method. And in particular, also we can answer the question about the lifetime, because it seems to be sufficient to observe such kind of vortex nucleation. Okay. For the last part of my talk, I will explain a theoretical project that is basically an application of rotating dipolar supersolids, in particular to observe glitches phenomena that are phenomena that usually are seen in neutron stars. So for this reason, let me start with a very general introduction about neutron stars. In particular, what are the main properties that we need to know to understand the connection with dipolar supersolids. So neutron stars have a gravitational mass that is 1 or 2 times the mass of the Sun. They have like a small radius. Usually it's around 10 kilometers. And the temperature are like orders of magnitude lower than the typical energy scale of nuclear matter. So because of these properties, they can be viewed as very dense and called the nuclear matter system, in which quantum effects are important. So how do we see them? Usually, they manifest as pulsar. So they are like highly magnetized rotating neutron stars that emits an electromagnetic radiation out of the magnetic poles that they have. And since the rotation axis and the magnetic axis are not aligned, but they are misaligned, from Earth we can see them like as a lighthouse effect. And so this allows us to basically measure with like very high precision the rotation frequency of the star according to the measure in which they are off pulse or on pulse. So you see really this lighthouse effect from Earth. So since it's rotating and it is emitting radiation, so we expect that this object would lose energy in time, and so also the rotation frequency should the rotation frequency should decrease in time. But every once in a while, you observe that this spin down is interrupted by a glitch. So this is a glitch, and this is like this discrete and randomly timed jump in the angular velocity of the neutron star. And these jumps are quite small. They are of the order of magnitude of 10 to the minus 12 to 10 to the minus 3. And the widely accepted mechanism for this phenomenon is believed to be a consequence of the internal dynamics. And in particular, it's believed to be like a hint of superfluid properties of neutron stars. So let me give a very general idea of the structure of the neutron star. So in particular, this is a section of the internal structure of a neutron star. The outer crust is believed to have a crystalline structure, so solid properties. The heart of the neutron star is the core, and it is believed to have superfluid properties. And in between the two, the inner crust is believed to have a coexistence of crystalline and superfluid properties. So you can see this is from this paper, they analyze the structure. You have this the presence of these crystal sites, but they are not independent because they are connected by this neutron superfluid bath that connects the crystal sites. And so this resembles a lot, it's very reminiscent of the supersolid phase that we have, in which we have these droplet sites that are connected by this superfluid background. So going back to the neutron star, the accepted mechanism to see these glitches, so this sudden spins up of the neutron star that is basically normally slowing down, is that as I said before, the outer crust is a crystal, and so it rigidly rotates at the observed rotation frequency. And the inner crust, because of these superfluid properties, it will lag behind, and so it also will store angular momentum in form of quantized vortices that, because of the presence of the lattice, will be pinned in specific positions. Then, during the slowdown process, the inner crust would lag behind until it reaches an out of equilibrium state. After this out of equilibrium state, it will release a sudden amount of angular momentum through a collective unpinning of vortices. And so this angular momentum that is released from the inner crust, it is absorbed by the outer crust. And this causes the sudden spins up of the glitch. So this is like the reason for this sudden spins up that I showed to you before. So since the inner crust resembles a bit the structure of dipolar supersolids, and since these glitches are like this inner crust is responsible for the glitches phenomenon, we can try to use dipolar supersolids as inner crust laboratories, so to simulate exactly the same dynamics. For example, we can take like this supersolid state with 19 droplets, and we can put it under rotation. So we can create our state in equilibrium in the rotating frame. It will host quantized vortices that you can see here from these holes, or here in the 3D version, these are like the vortex tubes. And these vortices are pinned in specific positions because of the presence of the droplet lattice. So as in the neutron star, we can simulate the slowdown process with a dissipative extended Gross-Pitayevsky equation. And most importantly, unfortunately, I don't have the time to go into the details, but we can implement a model for the feedback. So with this model, basically we are saying that during the slowdown process, every time that the supersolid loses a vortex, its angular momentum is reabsorbed by the solid part of our supersolid. And so with this, basically by solving in real time these two differential equations that are coupled, because the result of this differential equation is omega that then goes here, we obtain, for example, these results. So this is like our supersolid with the vortices. Now, if you focus on this, so a vortex is leaving, another one is taking his place, and also you have other unpinning of vortices, and this corresponds to the point in which omega, that is the rotation frequency, suddenly spins up. Now, again, if you focus on this vortex here, this leaves, the other one takes his place, also this other one is moving, so it's not an effect due to only one vortex, but it's something more collective. And again, you see that the omega spins up, and then you have this oscillation here. I will be back on this oscillation later. And here again, if you focus on this one, we have our third glitch. And again, the same phenomenon, the same spins up. So, I mean, these jumps are quite small. But if you look at the order of magnitude of delta omega over omega, that is the same quantity that I showed to you before for the neutron stars. So this is the order of magnitude. This has an order of magnitude of 10 to the minus 3. So it would be like a giant glitch compared to the numbers that we have in neutron stars. And like this model seems to be quite promising for the fact that we can't have access to the internal structure of neutron stars. But here we managed to really replicate the same physics. And here we can really have access both to vortex dynamics, to understand what is the unpinning mechanism, so what happens, and also to crystal excitations, because our crystal is not fixed, it does not co-rotate with the trap, but it's made of droplets, and these droplets are perturbed every time that a vortex goes out. And so we would really like to analyze like the shape of the glitch, and in particular the frequency of oscillation, the size of the glitch, and relate it to this crystal excitation, because maybe for neutron star, by looking at the size and of the structure of the glitch, we can infer something about the internal structure or the lattice that we can have inside. So with this, I come to my conclusions. I showed you how like the experimental realization of two-dimensional supersolidity opens the new possibility to have like a direct probe of the superfluid nature of the system. I showed you how magnetosteering offers a unique way to impart angular momentum to a dipolar system. And finally, I showed you how rotating dipolar supersolids offer the possibility to test both the vortex dynamics and the crystal dynamics during a glitch, in analogy to what happens in neutron stars. I would really like to thank all my team and also the external collaborators for all this project that I showed to you. And in particular, so Tom, Lauritz, and Wyatt are here, and they will present a poster. So if you are curious to know more about other projects we are working on or more about vortices, in particular about experimental details, I think they will be happy to answer all your questions. And last but not least, I think Francesca, Antoine, and Robert are organizing this conference in San Sebastian in September. It's about long-range interaction, so she thought it was a good moment to advertise this event to you. And thank you for your attention.
Thank you very much, Elena. So, questions?
Thanks for showing us nice results. I was wondering, the time between glitches, what does that exactly depend on?
Yeah, that's a good question. Because you can't really predict when the system will go in this out of equilibrium state, because the thing is that because of this superfluid character of the system, it will a bit lags behind compared to like the ground state of the system for that specific value of the rotation frequency that you have. So yeah, I think really the glitch is defined to be something that is like randomly time distributed. So
it looks like they come like in similar distances. Is that true? Or
yeah, it's not. I mean, yeah, it's not true. It's not true in general, I would say. I mean, I think I have. Wait. I have. I don't know if I put. Sorry. I don't know, I have other results here for different scattering length, but like, for example, here the time scale is much longer than this true. So yeah, it's not. Yeah, exactly. And also, yeah, please.
Thank you. This is all cool stuff. I mean, I have a question about the neutron stars as compared to this. I mean,
yes.
Here you see that quantum by quantum is absorbed by the solid, and then you see basically one vortex at a time.
Yes.
Leaving the system. Is this also true for the neutron stars?
No, a neutron star,
I mean, one quantum is probably such a small quantity that
so
you cannot detect it. So how does it work there? That basically, do they like team up and have some whatever collective process that thousands of vortices or many more leave at the same time? Or how can I think about this?
Yeah, so in neutron star, I think the number of vortices that is expected to leave is like 10 to the 7 for each glitch, because like the time scale is completely different. What we managed to simulate here is like one vortex leaving or two vortex leaving. So in this case, this other simulation, we also have two of them leaving, and other inside that are moving. And so since they are moving at a different radius, the angular momentum is redistributed. No? So like it's still a collective thing.
But can you imagine, also looking at your simulations, that the distortion due to one vortex that is left behind sort of makes it easier for other ones as well, and so on.
Yeah, exactly.
And but okay, 10 to the 7. Yeah.
Yes,
wow.
But yeah. Yes.
Okay, thanks.
Very nice talk, very interesting. So just wondering, for measuring this change in frequency, what would you do in the experiment? How do that you let the system expand? What would be the way to do it?
So you mean for the glitches? For this? Yeah, so okay, at the moment, this is like a theoretical proposal, also because of this model for the feedback. So in principle, you would like to, because at the moment now we are like say, okay, the angular momentum that is released by the vortex is kind of reabsorbed by the solid part of our system. So there is this model behind that, I mean, it's not trivial how to implement it in experiment. I think one thing we thought was to like extend these to two component systems in which one of the two components drags the other one. And so you would be able to measure, like the angular frequency of the other component compared to like the relative frequencies between the two. But at the moment we don't have like a clear answer for that.
So regarding the vortex nucleation that you showed, have you seen vortex melting at all?
You mean annihilation?
Yes.
No, because they all have the same like vorticity with the
So
same. They are all the same sign because we are rotating the magnetic field always in the same direction, and they have all the same.
So they remain robust.
Yeah.
Okay.
Yeah.
And what are the quantum effects of these vortices compared to the normal vortices that we know from superfluids?
What do you mean? Sorry, like.
I mean, do they? So here you have, let's say, the quantum fluctuations, right?
Yes.
So what is the difference between the vortices that we know from normal superfluids? Do they differ in their core size? They are more
you
shallow?
You mean super solid phase and normal superfluid phase?
Yes, the vortices.
Yeah. So I think the one difference, so they are the same. They are the same topological defects. The circulation is still quantized. The angular momentum that they carried is less than 1 h bar. Like it's less in general. So this is one, I think, the main difference. But I mean, they are the same topological defects, topologically protected. So yeah.
And did you try to do this trick of rotating at a smaller frequency and then changing the scattering length, entering into the super solid, and getting the vortex? As
you mean the opposite,
with Sandro?
like?
So basically, not only just the trick of quenching into the super solid as a way of seeing the vortex, but as a way of nucleating the vortex.
Nucleate? No.
Because in that paper with Sandro, basically, we have these two parts basically, in which you quench at the same time as you rotate, so to say.
Yeah.
And in this way, you see this less than h bar, as you say.
Yeah. I see what you mean. Yeah. No, at the moment we are just. I think we are just rotating the super solid, trying to create a vortex there, and then just quenching just to see, to detect what we actually created before.
And just one question, because I have 1 minute. So, in the way of rotating just with the dipole, so to say, the pictures that you showed before in the non-super solid regime, you create many vortices. So it's a kind of very violent effect in some sense. Is there a way to? So, is it possible to do this rotation with the dipole and at the same time creating just one vortex?
I think so. Yeah.
Is it as controllable as just rotating the trap? That's my.
I mean. Okay, so all the movies I showed before and all the pictures, so first it's rotating at a frequency that is 0.75, the trapping frequency. So of course, rotating at lower frequency would reduce the number of vortices, but it's also true that it would take more time for vortex nucleation. So I think we decided that because it was faster enough. So in principle, yeah, you can control it, but it would take more time to reach it. Yeah.
Okay, so quarter. Yes, very good. Thank you very much to Elena and to all the speakers.
Yeah. So now we will have the poster session at Rotunda. So just follow us. Yeah.
Thank you.
So I have some questions.
Yes.
Maybe in the poster session.
Yeah. Of course. Yeah, I have time.
Very nice.
Thank you.
Congratulations.
Thank you.
This change in the angular momentum is very small. It's very difficult to see, even by bare eye in the picture.
In which?
The glitches.
Yes.
Just by bare eye, it was not possible for me to see the change in the momentum.
Yeah. No. It's small.
Right?
Yeah. It's small. It's small. Yeah. That's why.
I'm still wondering about this time between glitches. Doesn't that reflect somehow the size of the system? You have your crystalline part, and then in between are the vortices, and the vortices have to travel sometimes.
Yeah, this for sure. Yes.
That must be.
This I agree. Yeah, this I agree because
looking at your data when you showed them once more,
it
I
was,
still think
it's yeah, I think
not the same, but
it's very close.
It's
yeah.
kind of close. For different rotation frequencies, it's different.
Yes.
Yeah, but for a given one, it seems kind of not so irregular. Yeah?
So for sure, the thing is that maybe so the system would like not so like the super solid system would like to reach the ground state in the rotating frame, and could be that during the slowdown process there's like one extra vortex, and so I mean. I think it's not automatic to say that like during the slowdown process you would have same time. I don't know. It depends on.
It also depends on the spinning force itself.
Of course, yes, yeah. That's why I also show like the results for different scattering length in which the vortices are more or less pinned in the specific position, and so they need more or less, out of equilibrium configuration to go out.
Somehow all this wisdom is in your equation, right? This time scale must somehow be there. Maybe, I don't know, one can find a way to dig it out of the mathematics. Another thing I was wondering about, if you look at the neutron star, you have this lighthouse effect, and there's energy radiated away, and it's clear that should have a consequence. In your case, are you including in your description, well, you describe things with the GP equation, but there's a thermal cloud around.
No, I mean, it's
and
like
then you interact. I mean, this is typically how the vortices come out. If you don't have an interaction between the thermal cloud, then that doesn't happen.
Yeah, so what we do is we perform this dissipative Gross-Pitayevsky equation. Basically, instead of evolving the wave function in real time, we evolve it in complex time. So this is kind of having it's like having a temperature, a finite temperature to the system. The Gross-Pitayevsky equation is at 0 temperature, but introducing this complex time is like you are evolving the system, but at the same time the system would like to dissipate some energy otherwise the energy would be like constant. And so this is like the way in which we simulate the slowdown. The slowdown process. Also because the trap that we use in order to have more similarities with the neutron star is cylindrically symmetric, and so otherwise without this dissipation, like the system would not react to a change of omega because it's not like coupled; it's completely symmetric, and so that's why we implemented the slowdown.
I got it. I understand.
Okay.
Okay, thanks.
No, you're welcome if you have other questions.
Very nice talk.
Thanks. Also yours was nice.
Because you are like mixing two things. One is the rotation, and the other is the dipole interaction. It's like it doesn't look like externally like a good idea. I don't know how to mix the two things. No?
Yeah, there is Yeah, I don't think it's the best way to generate the one nice thing it gives you is it gives you so you're trying to investigate properties. Like so the vortex strike, for example. I think it only gives weight to dipoles with the vortex. So even though you're rotating the trap, you have to rotate the E field as well. So you can But actually, I mean, to your question here, like, you can make one difference. The best way to do it is to rotate the soup side and then go into the AC ratio. Because we've seen it in the experimental images so far. We've always seen one vortex left behind. It's a bit of an extreme way of doing it.
The question that you were making about how the LHY behaves when you start to rotate like that, and this is a very good question.
So I've asked this question to some before, so I think if you actually derive the LHY contribution and you have this anti-dipole interaction from the beginning, then you do come down to just this modified version where you just essentially put in this factor into EDD. And it becomes EDD. Yeah. So
But the question
yeah, but you've got to be faster than this.
But what happens in the intermediate region, because now you are protected like this, if you rotate slowly, you are in this region, where you use the LHY in a given way. If you rotate the fast, you use the LHY in the other way. What happens in the intermediate region?
No idea.
It's very similar to this, this coherently coupled that when you do this driving, you change the nature of the LHY. Here, as a function of this rotation, there must be a change in the nature of the LHY. Change at least the value of the LHY, which changes from here as a function of rotating frequency.
Sage, okay, man kann da natürlich noch immer, aber ich belasse es jetzt, und dann gebe ich diese komme ich einfach darauf, also dann, genau, dann zeige ich hier den Marchand-Seitenresultat und dann zeige ich den Helix-Seitenresultat hier.
That you modulate the flashback resonance and you create some momentum distribution that's secular. If you match the maybe some energy scale of the interaction of the modulation and the interaction.
Hier zeige ich auch nur ganz wenig. Diese ganzen habe ich alle in
The last part is very interesting. Never thought about it.
Und hier ist jetzt genau die Frage, was braucht man, habe ich ja gerade erzählt, was man braucht. Also den Body und Drive, den haben wir jetzt, aber wir lassen es nicht, und den brauchen wir noch dazu. Und dann, ja, das fällt raus, und dann, das habe ich noch nicht, und dann zeige ich das. Genau, aber soweit habe ich das im Prinzip. Ja. Genau. Ich glaube, genau, dann kommt aber das noch natürlich die Frage. Ja. Warum kriegt man da, also sehen wir da was anderes? Ja. Das macht das nicht weit. Da verwurschtel ich im Prinzip diese zwei Slides noch. Das verstehe ich. Was ist denn das?
Ja, das ist, weil vorher dieses Argument, dieses analytische Argument hier, das ist für den Zwei-Atom-Case. Und auch das nächste hier ist der Zwei-Atom-Case.
Ach so, und das ist für...
Dann haben wir gesagt, wir nehmen 6 Atome und die analysieren den vollen Windoperator und schauen, wie die die Population in den einzelnen Zuständen ist. Und wie ist auch wieder alles gemixt. Es ist aber jetzt gar nicht so wichtig.
Nee, aber das ist okay, ich zeige das dann vielleicht ohne den ganzen...
Ja, also da geht es nur darum, dass man sagt, das ist nicht nur für 2 so, sondern auch wenn man das auch aufskaliert, dann eben passiert, also mixt sich das alles.
Okay, also ein bisschen aufräumen muss ich noch.
Ja,
aber so weit habe ich das jetzt. Okay, alles klar, super, vielen Dank. Aber das ist nur nochmal abklären.
Nee, also das ist, glaube ich, recht kohärent und gut dann, ja. Das so zu verbinden, ja. Und ich glaube, diese letzten Dinge, die kann man ja relativ schnell einfach mal so zeigen.
Das Einzige, was ich wahrscheinlich noch dazu tue, ist noch ein Slide mit Spin Squeezing, weil da brauche ich vom Handshell noch die Bilder dazu und das Bild dazu, ansonsten nicht.